Okay, so welcome to the Military Industrial Museum feature presentation of a huge amount of information. What I have here is a easily obtainable physical copy, more or less. Plus, well, actually, it's more. It doesn't just have what we're going to review here on the show, but it has compilation of other works of and about Nikola Tesla. So yeah, it's just a huge. So this book, I'll put a link in the description. There's the ISBN if you want it, and then this is what it looks like. It comes in a gilt folio format. It's supposed to be leather, and the manufacturer origin is China. So, pretty good book, if you ask me. It's got a lot of illustrations and such, but this is a book you can study and really absorb the information, and it kind of, it's kind of handy and whatnot. But the main thing is you can attain this, a physical copy, and go like that. So I'll put the link in the description where to get it. For those that can't afford a physical copy, I'll put a link in the description for a digital version of what we're going to go over, and you can study it that way. So real quick, people have different ways of learning. Some use their eyes primarily, some use their nose, some use their hearing, some use their sense of touch, tactile. So the physical version, that's for the tactile folks that want to flip through pages. It's also for the folks that learn via smell. You can smell the book and like that. Also, you can hear the book. When you tap on it, it makes noises and stuff. So it's all about learning styles and compatibilities. Everybody learns differently. So what we're having here is a video presentation of what's in this book, at least the main contents. Like I said, this has some extra stuff in it. But what I want to tell you is, for me, my learning styles vary, like even through life. Like I used to be able to read a book a day, no problem. Now, attention spans, not just for me, but for everyone, have declined over stimulation or something. And so it's very hard for me to pick up a book and just read it outright. So Google Notebook LM came up with a new format called cinematic, and so you can take rote text, ROTE text, and input it into the cinematic function, and it will magically make a little video / presentation / dictation of what's going on. So what I did was I took each chapter and I fed it into the cinematic function. Presently here, March 27th, 2026, you only get 20 generations a day, and that's if you have the Google Ultra plan. And so it's a rarefied thing. It's pretty expensive. So because of that, I ask you to support my channel. Maybe use the link and buy the book. It might help yourself to study this stuff. It depends on your learning style. If your budget's not good, just subscribe to the channel. It doesn't cost you anything. And hit like and stuff. If not, it's just like watering a tree. If you want the tree to be around, you better make sure that you take care of it. Same with this stuff I put out. So, but yeah, most people will not be able to handle this information. Right now, I'm rendering the video. It's over 3 hours. It's a doozy. So hopefully we'll keep coming back to it and studying it. The idea is check out the video, flip around, see what you want to look at. If you find something interesting, you can go back to the physical version or the digital version, the text based, and there's pictures and stuff here and there too, and have different learning formats to absorb the information. And then repetition's a thing too. You can watch this video over and over again. Maybe you can fall asleep to it or whatever, and start picking up the information. I was watching a little bit of scenery, and the emphasis on electrostatics was like a revelation to me, because I didn't put that together. I vaguely understood, but as you'll be able to listen from the lesson, the electrostatic principles enormous for the single wire transmission. So anyway, yeah. Well, so there you go. In a nutshell, I don't want to have a huge intro that'll be boring and repetitious and stuff. But like I said, this is a book. It's called The Autobiography of Nikola Tesla and Other Works. But in this book, the meat of this book is that presentation, which you'll see here soon. And you can get yourself a copy. I bought this. This is a used copy. I think I paid about $20 for it. The new copies, they're quite a bit more than that. But yeah, I feel like one of those college professors telling the students, "Hey, this is a book you need to buy," and then they're feeling bad about it. But if you get the education, and I remember one account by one AI said, this is a basic electromechanical course, more or less. If you can understand and study this stuff in its entirety, you'll have a very solid electromechanic understanding, obviously. And obviously there's other factors going on too that you'll have an understanding of, such as electrostatics and things like that. So yeah, enjoy, and I hope that you subscribe to my channel, Military Industrial Museum, here on YouTube, and otherwise support my work. So yeah, I've been wearing a cap, and that's why I got this flyaway hair. Whatever. A lot of people let themselves go, that they have their head in the clouds, or their nose in the book. I have that issue too. Like, I can either put a lot of money and time into self-care and presentation, or I can get to the meat of the matter, which is put this video out, and hopefully I get a lot of subscribers and fans and things out of it. But who knows? Just the way the general public is, their attention spans, they just can't handle it. But we'll see. It's up to you whether this experiment works or not. I'm gonna try this format on a few more iterations and different subjects and topics, and we'll see what flies and what doesn't. But if I ever want to study this stuff, this is how I would study it. I would get the physical format. I'd watch the video. I check out the digital side, from. I think I'll put a link to the Internet Archive. There's a digital version. There's actually many. You can take a pick, but I'll put the one that works. And so you'll be able to listen. You'll be able to watch. If you get a physical version, like this book, you'll be able to smell it. You'll be able to touch it. And you can touch a screen or whatever too, obviously. But the tactile function is a function of learning. And with a physical version, you'll be able to highlight things and mess. There's different learning formats, and it's super important with Tesla's work that you find a learning pathway or multiple pathways because he was sort of as he talks about, his learning and expression were divergent. So you got to put that into a factor, trying to learning things, and then from his realm. So I think you're picking up what I'm laying down. So without much further ado, I present the Military Industrial Museum homage to what you see here. Read the title. The title escapes me, honestly. Like I forget what the title is. It's like 3 or 4 different terms thrown into one. That's how zonked I am. I'm sorry. I haven't been sleeping well, but you get the drift. So enjoy what you can. Come back later. It's like snacking. Just snack on the information for now. When you get really hungry, come in and do a deep dive. It's there for you. But just window shop and snack and sample for now and see what you like. And if you like it, save the video, come back, whatever you need to do. Okay, thank you and enjoy.
A polyphase synchronous motor maintains exact speed by locking its rotor to the frequency of the AC grid. At 0 RPM, the motor fails. The alternating magnetic poles of the stator push and pull the stationary rotor with equal intensity, resulting in 0 net starting torque. The alternative is the asynchronous induction motor, or torque motor. It generates massive starting torque from a standstill by inducing current directly into the rotor. However, an induction motor requires slip, a difference between the magnetic field speed and the rotor speed. This slip prevents it from ever reaching true synchronous speed and causes efficiency losses during high-speed operation. These two machines have mutually exclusive benefits. One provides torque at a standstill, while the other provides efficiency at locked speeds. In the 1890s, the engineering challenge was to bring a high-efficiency synchronous rotor up to speed under heavy industrial loads without an external mechanical engine. 19th century power distribution required a machine with these contradictory physical properties, forcing engineers to look beyond mechanical design for a solution. Nikola Tesla addressed the motor starting crisis by applying his foundational work in polyphase alternating currents. In Chapter 20X, Tesla outlined a specific premise: the physical combination of a torque motor and a synchronizing motor into a single unit. In this mechanical architecture, both motor armatures are rigidly mounted to and drive the same central shaft. The genius of Chapter 20X lies in the dynamic electrical circuit used to control these coupled armatures. The baseline schematic features 2 distinct motor symbols and a network of parallel shunts controlled by switches labeled P', S, and T. Tesla bypassed the magnetic limitations of the iron by shifting the problem into an intelligent electrical state machine. The electrical topology begins with the armatures of the torque motor and the synchronizing motor wired in series. Switch P' creates a shunt pathway that can completely bypass the synchronizing motor. In state 1, the objective is maximum power to the torque motor to overcome static friction. The operator initiates the system by closing switch P' before applying line voltage. Current takes the path of least resistance through the shunt, isolating the synchronizing motor. The torque motor receives full line voltage, maximizing asynchronous starting power. The heavy shaft begins to rotate under the brute force of the torque motor. In state 1, the electrical architecture disables the synchronous capabilities to optimize the system for raw starting torque. State 2 triggers as the rotating shaft approaches its maximum asynchronous speed, limited only by the torque motor's slip. The synchronizing motor must be energized before it can lock into the AC waveform. The operator initiates the transition by opening switch P'. Removing the shunt forces current to flow through both the torque and synchronizing motor armatures in series. Because the motors are now in series, the available voltage is split, which reduces the motive power of the torque motor. The synchronizing motor's magnetic field becomes active, while the rotor is already being mechanically spun by the torque motor. The spinning rotor poles begin to align and pull into step with the rotating stator field. State 2 acts at an electromechanical bridge, using the torque motor's momentum to bootstrap the synchronizing motor into the grid's exact phase. State 3 begins once the synchronizing motor achieves phase lock, pulling the heavy shaft to its exact synchronous speed. At this speed, the torque motor produces no motive force and acts only as an electrical and mechanical drag. The final sequence involves closing the secondary switches, S and T, to form a new shunt around the torque motor. The current now completely bypasses the torque motor. full line voltage is now dedicated entirely to the highly efficient synchronous machine. The system runs at absolute constant speed, regardless of normal load fluctuations. Tesla's topology deletes the torque motor from the circuit once its mechanical purpose is fulfilled. Tesla successfully granted a synchronous machine the ability to start itself under heavy load. Comparing these three distinct topologies shows the dynamic nature of the circuit. This system functions as a manual state machine, directly mapping electrical routing to shaft RPM. Tesla proved that seemingly insurmountable mechanical limitations could be circumvented through intelligent circuit routing. This topology supported the massive industrial rollout of polyphase AC power during the 1890s. These principles of motor shunting and series parallel transitions provided the conceptual groundwork for 20th century automated motor controllers. Modern variable frequency drives, or VFDs, which are solid-state controllers that manage motor speed by varying frequency and voltage, eventually replaced these mechanical switches, though the underlying logic of state-based control remains. The Chapter XX motor stands as a masterclass in dynamic, programmable electromechanical architecture. In the 1880s, early direct current networks expanded rapidly across cities, but faced a severe engineering challenge. For instance, when large electrical loads were switched on, neighboring lights connected to the same grid would severely dim. For the consumer, the experience was highly erratic. The simple act of turning on an appliance could drain the power from a machine running next door. This happens because of a core electrical principle. Adding loads in parallel lowers the overall resistance of the circuit. If the generator's mechanical input remains static, that drop in resistance inherently pulls the system voltage down. This exposes a secondary physical problem, known as armature reaction. When heavy currents flow through the spinning armature of a generator, they create their own intense magnetic field, which physically pushes against and distorts the primary field generating the power. Engineers needed a way to achieve dynamic, real-time voltage regulation. They had to counteract these magnetic distortions instantly, using heavy mechanical linkages and basic electrical properties. Without active, automated regulation, early direct current grids struggled to adapt to the fluctuating consumer demand they were built to serve. Before his celebrated shift to alternating current systems, Nikola Tesla spent his early career directly tackling the inefficiencies of direct current. In his collected writings from 1885, Chapter 38 outlines a mechanism titled Auxiliary Brush Regulation of Direct Current Dynamos. His thesis outlined an electromechanical feedback loop. He designed a machine that could continuously sense its own electrical output and physically alter its internal geometry to correct any drop in voltage. Tesla noted in the text that, with this specific regulator properly adjusted, massive grids of arc lamps could be toggled on and off with scarcely any perceptible difference. Achieving this required a generator to measure its own efficiency in real time and translate that electrical data into the physical movement of its own internal components. By linking output directly to architecture, the burden of electrical stability shifted from a human operator pulling levers to the physical laws governing the machine itself. This diagram shows the baseline architecture of a standard direct current dynamo, a central commutator rotating between two magnetic poles, flanked by two main brushes. The commutator spins rapidly, converting generated energy into a steady direct current sent to the grid. Current collection is most efficient along a specific geometric plane, the neutral axis. Under a steady load, this axis sits perfectly perpendicular to the magnetic field. The brushes rest exactly on this line. But watch what happens when a sudden heavy electrical load is applied. A massive surge of current flows through the spinning armature, generating its own powerful magnetic interference that warps the primary field inside the machine. As the magnetic field distorts, the neutral axis physically shifts diagonally, leaving the fixed brushes behind in the wrong position. Bridging the wrong commutator segments triggers severe electrical sparking at the physical contact points. This misalignment destroys efficiency, causing an immediate, severe voltage drop across the entire connected lighting grid. A static machine architecture cannot maintain an efficient interface with a dynamic electrical load. This schematic details Tesla's architectural revision, the addition of a third auxiliary brush touching the commutator. When first energized, the main brushes rest on the neutral axis. The third offset brush draws a fractional baseline current. This collected electrical potential depends entirely on its physical distance from the main brushes. That control current routes into an electromagnetic solenoid, a coil of wire that generates a magnetic field to physically pull a metal core. As external grid demand spikes and the neutral axis tilts, the voltage differential registered by the third brush instantly changes. This electrical fluctuation immediately alters the strength of the magnetic pole inside the solenoid. The solenoid's core is physically attached via a lever to a movable yoke, a rotating collar holding all three brushes. When the shifting voltage causes the solenoid to pull, it rotates the entire yoke, sliding the brushes to chase the shifting neutral axis. By tying the brush's physical position to a real-time electrical sample, the dynamo dynamically regulates its field excitation to match the exact grid load. But directly coupling electrical variance to a physical lever creates a mechanical flaw. Electrical transients trigger at the speed of light. The brass yoke holding the brushes, however, has significant physical mass and inertia. A massive load spike causes the solenoid to jerk violently. Driven by momentum, the heavy brass yoke swings too fast and overshoots the neutral axis. Missing the axis causes the voltage to drop too far in the opposite direction, triggering a reverse pull. The machine gets trapped in a destructive physical oscillation known as hunting. To strip away this erratic movement, Tesla integrated a mechanical dampener into the system, the dashpot. A dashpot uses a metal piston moving through a sealed cylinder filled with a highly viscous fluid, like oil. It operates strictly on the physical principle that fluid resistance scales directly with velocity. The thick oil allows the piston to glide smoothly if the adjustment is slow, but it aggressively fights back against sudden, violent jerks. By attaching the dashpot directly to the actuator lever, the violent pull of the solenoid is intercepted. Kinetic energy is absorbed, forcing the heavy yoke into a smooth, controlled rotation. The dashpot acts as a mechanical low-pass filter. It ignores the rapid, erratic electrical noise of the grid and translates only the sustained changes into stable, precise physical movement. This diagram shows the complete, integrated control system functioning as a single unit. A massive load hits the external grid, demanding instant power. The magnetic field distorts. The third brush registers the exact voltage differential and alters the current flowing to the solenoid. The solenoid pulls hard, but the dashpot intercepts the force, easing the yoke steadily along the curve of the commutator. The brushes lock directly onto the newly established neutral axis. Sparking vanishes, and the voltage distributed to the grid holds perfectly steady. Automation requires the machine to sense an error and then precisely govern the physical rate of its own correction. This 1885 design stands as a rigorous, early exercise in applied control theory. Modern power electronics achieve this exact same voltage regulation instantly, relying entirely on solid-state transistors with zero moving parts. Achieving stability using only magnetic pull and fluid drag required turning the physical properties of inertia and friction into precision tools for electrical regulation. Developing this automated direct current hardware forced engineers to deeply model shifting electromagnetic fields. This exact mathematical rigor paved the way for Tesla's later polyphase alternating current systems. Long before the silicon chip, the stability of the modern electrical grid was forged in the precise mechanical dampening of raw electrical power. Polyphase induction motors operate on a precise electromechanical rhythm. They rely on multiple alternating currents, which are electrical currents that periodically reverse direction, offset from one another in time. By staggering these currents, the motor generates a rotating magnetic field. This creates the continuous mechanical push required to drive the rotor in a single direction. A single-phase alternating current source works differently. Because it only delivers one wave of current, the resulting magnetic field pulses in strength, but remains physically stationary. Without that rotational offset, the magnetic field pulls on the rotor symmetrically. The rotor experiences equal, opposing torque forces that cancel each other out. The result is a mechanical stall. The rotor vibrates in place, locked at a zero torque point, completely lacking the directional bias needed to initiate rotation. Engineers typically solve this starting problem by wiring in external components, like starting capacitors, devices that store and release electrical energy, or by splitting the phase across separate copper coil windings. These workarounds require additional copper wire, demand extra circuitry, and more physical volume, adding significant cost and complexity to the motor's design. Generating continuous, self-starting rotation from a single AC wave without any external electrical components is a problem of artificially dividing time using the physical properties of the materials themselves. In the 1890s, Nikola Tesla's research into alternating current architectures led him into highly unconventional electromechanical investigations. His laboratory was an environment of rigorous testing, dedicated to pushing motor designs past the limitations of standard multi-phase systems. A detailed account of these experiments survives in an 1894 volume titled The Inventions, Researches, and Writings of Nikola Tesla. Edited by Thomas Commerford Martin, this book serves as the definitive 19th century record of Tesla's early engineering proofs. Chapter 12 outlines a device called the magnetic lag motor. Tesla claimed this machine solved the single-phase stall using material physics rather than complex electrical circuitry. The core thesis of the chapter relies on hysteresis. Hysteresis is the inherent delay, or magnetic lag, exhibited by iron when exposed to a changing magnetic field. Standard electrical engineering actively avoids this phenomenon. Tesla took an electromagnetic inefficiency and recontextualized it as the primary motive force driving the rotor. When a ferromagnetic material is exposed to an alternating electrical current, its magnetic alignment reverses with each cycle. Engineering textbooks classify this resistance to changing polarity as core loss, useful electrical energy wasted as heat inside the machine. This BH curve shows the hysteresis loop. As the electrical sine wave flows along the horizontal axis, the magnetic flux density wave shifts right, peaking only after the electrical current has reached its maximum. The iron core physically resists the change in current. Its magnetic state is remembering a previous electrical state, which creates a measurable temporal delay. Tesla identified this specific delay as magnetic lag. At the time, physicists like Professor William Ayrton were only just beginning to advocate for the reality of this phenomenon. In high-quality iron, this lag is vanishingly small, yet it remains a persistent, measurable physical reality within the metal. Tesla realized this delay functioned as a phantom second phase. The iron itself could be harnessed to stagger the timing of the magnetic field. The challenge lay in scaling the effect. As the frequency of the alternating current increases, maintaining a useful degree of magnetic lag becomes increasingly difficult. But properly tuned, the temporal delay between the electrical current and the resulting magnetism provides the invisible secondary force required to break the symmetry of a single-phase motor. Tesla translated this abstract wave physics into strict physical geometry, as illustrated in figures 54 and 55 of Martin's text. Alternating current energizes the base, flowing into the heavy stator cores. If iron magnetized instantly, magnetic pole would peak exactly when the rotor and stator perfectly aligned, locking the motor in place. Due to hysteresis, magnetic attraction is delayed. The peak attractive force occurs a fraction of a second after electrical current peaks. The rotor's momentum carries it past the stator's center line before the magnetic field reaches maximum strength. The resulting dynamic is a continuous chase. The peak magnetic pole always trails the physical position of the spinning rotor. Unlike polyphase motors, which trigger coils in succession, this delay manifests attractive effects simultaneously across the entire geometry of the motor. The literal angle of the magnetic pole is the physical manifestation of the electrical phase shift. The temporal delay born from hysteresis creates a spatial asymmetry. The iron's delayed response hard-codes an angle of torque directly into the machine. This design means the magnetic lag motor operates as a physically tuned instrument, rather than a general-purpose machine. The precise degree of magnetic lag is a direct function of the iron core's mass, its overall size, and its specific magnetic permeability, which is the measure of a material's ability to support the formation of a magnetic field within itself. To maintain torque, the core's physical dimensions must be locked to the alternating current's frequency. If the frequency is too high for the iron's mass, the lag becomes too great. The phase shift pushes past optimal, collapsing the torque vector. Tesla explicitly noted this limitation in his writings, warning that the proper relations between mass and alternating frequency must be preserved to secure the best results. This strict physical dependency limits where the motor can be deployed, but it proves the exact calculated nature of its electromechanical design. In the 1890s, sourcing and casting iron with the precise metallurgical properties required for this specific timing application was a severe manufacturing challenge. The machine functions as a hardware-based phase shifter. The iron block itself performs the computational work of timing the magnetic field. Bringing these theoretical components together yields a machine that sidesteps conventional electrical engineering. Tesla exploited the atomic properties of ferromagnetic material to bypass the need for external capacitors or complex split-phase circuitry. He recognized that phase separation was an electrical problem that could be solved mechanically through the deliberate introduction of mass. The magnetic lag motor proves that an electrical phase shift is a physical property of matter, one that can be weighed, cast in iron, and harnessed to drive a machine. In 1893, electrical engineering was a discipline of physical brute force. The industry obsessed over moving massive amounts of low-frequency alternating current across heavy copper wires to power immense iron dynamos. Low-frequency alternating current is an electric current that periodically reverses direction, typically at a rate of 60 times per second. When Nikola Tesla arrived in Philadelphia that February, the scientific elite expected him to expand on this heavy physical infrastructure. The audience at the Franklin Institute had gathered to see the man who invented the AC motor. They anticipated complex circuit diagrams, commutator specifications, and raw power metrics. Tesla bypassed hardware entirely. He stepped to the podium and opened his highly technical lecture with a physiological treatise on the human eye. This biological opening served as a deliberate redefinition of the starting point for electrical engineering. Standard engineering at the time followed a linear pipeline. It began with the power source, the generator, and ended with the mechanical output. Tesla reversed this sequence. Instead of starting with the power source, he started with the ultimate destination of the energy. To engineer new artificial light, he reasoned that physical hardware had to be dictated by the biological receiver, the pupil, and the optic nerve. Treating human biology as an engineering axiom forces a designer to ask different physics questions. Instead of asking how to push more current through a wire, Tesla asked what specific physical signal the eye was naturally tuned to detect. The construction of the transmitter could only begin once the receiver had been fully reverse engineered. Tesla described the human eye as an organ of inconceivable sensitiveness and discerning power. To Tesla, the human eye's lens and retina functioned as a signal transducer. It converts one form of energy, like light, into electrical impulses. External frequencies hit the retina and are instantly converted into electrical signals, traveling along the optic nerve. Tesla connected this physical sensitivity to human intellect, framing the brain as the ultimate central processor. Mechanical sensors available to electrical engineers in the 1890s were heavy, crude, and could only detect massive, slow-moving currents. Yet biological evolution had already produced a mechanism capable of capturing wave frequencies oscillating billions of times per second with high efficiency. If the eye is a perfectly tuned receiver, the electrical engineer's task is to identify the physical signal it was built to detect and then replicate it synthetically. Identifying that elusive signal required Tesla to look deeply at the empty space between objects, where light actually travels. Late 19th century physicists theorized the existence of the luminiferous ether. The ether was proposed by scientists as an invisible, continuous medium that entirely filled all space and connected all matter. Tesla explicitly rejected gross matter, like physical particles and heavy copper wires, as the primary vehicle for transmission. Energy transfers in two ways, through mechanical particle collision or propagating as a smooth, continuous wave through an unbroken field. Low-frequency current requires the brute friction of physical wires. High-frequency waves pass through this continuous medium effortlessly, radiating outward without interference. Tesla stated this as a fundamental law in his lecture. Throughout the infinite universe, all has to move, to vibrate. Tesla moved past the mechanics of physical wires to focus on a continuous, vibrating medium, the only environment where high-frequency electromagnetism could exist. Universal vibration maps directly onto measurable electrical frequency, calculated in hertz. Hertz is the standard unit of frequency, representing the number of cycles per second. The standard low-frequency alternating current used in the 1890s vibrated at 60 hertz. This rate runs heavy motors, but fails to produce efficient artificial light. This chart shows the electromagnetic spectrum, the entire range of all types of electromagnetic radiation. On the far left is industrial AC power at 60 hertz. Far to the right is visible light. To generate light using 60 hertz current, engineers forced it through a resistant filament until the metal turned white hot. The electrical vibration converted into heat before it reached the threshold of visible luminescence. Out of the entire electromagnetic spectrum, the human eye is only capable of perceiving a tiny sliver of high-frequency vibrations. A standard incandescent bulb wastes energy generating low-frequency heat, rather than targeting this specific high-frequency band. True efficiency in artificial illumination requires an engineer to bypass heat and agitate the medium at the exact rates the human eye evolved to detect. Reaching these vibration rates required physical hardware that moved away from the mechanical limits of the 19th century. Traditional dynamos relied on heavy spinning magnets. Spinning a mechanical armature fast enough to generate millions of cycles per second would cause the metal to physically rip itself apart. To overcome this limit, he invented the Tesla oscillator. An oscillator is a non-rotating device that produces a periodic electronic signal, often at very high frequencies, without mechanical rotation. The oscillator functioned as the synthetic counterpart to the biological eye. It was a transmitter tuned to match the extreme sensitivity of the receiver. By applying these extreme frequencies to glass bulbs, Tesla generated light through phosphorescence. Phosphorescence is a type of photoluminescence, where a material emits light without generating heat, continuing to glow even after the excitation source is removed. These bulbs glowed without any burning filament. The biological and physical principles outlined in his lecture became the strict design constraints for his new hardware. Tesla's engineering sequence started with the eye, moved through the medium, and resulted in the high-frequency oscillator. This research into high-frequency currents moved from lighting vacuum tubes to commanding massive potential energy discharges that filled entire rooms. By focusing on high-frequency waves instead of physical wires, he paved the way for modern fluorescent lighting and the field of wireless transmission. Modern engineering often breaks problems down into specialized disciplines. Tesla approached hardware design as an extension of natural systems. Tesla's work treats the AC motor and the high-frequency oscillator as technological mirrors of human physiology, utilizing blueprints that evolution had already optimized. Tesla's earliest triumph with the rotating magnetic field was eliminating the need for mechanical brushes, components that sparked violently and degraded under constant friction. Removing the brushes solved the sparking issue, but optimizing these early alternating current motors for industrial power presented a separate, massive hurdle. To achieve continuous rotation, engineers required precise control over the phase, the exact timing and synchronization of the magnetic pulses inside the machine. Without a mechanism to deliberately stagger these magnetic pulses, opposing forces would collide. Instead of spinning, the motor would merely vibrate in place. Solving this timing issue without relying on external electronic circuits defined the engineering landscape of early polyphase motor design. In the early 1890s, Nikola Tesla approached this problem from a perspective that favored physical architecture over circuit complexity. His findings are preserved in Thomas Commerford Martin's 1894 record, specifically within Chapter 4, Modifications and Expansions of the Tesla Polyphase Systems. Tesla proposed that electrical phase could be manipulated by engineering physical asymmetry and specific material resistances directly into the motor's frame. To see how these mechanics translate into physics, we will digitally rebuild this specific Chapter 4 motor from the ground up. Tesla's method translated electrical timing requirements into a specific physical layout, allowing the motor's own structure to resolve the phase conflict. Construction begins with the stator housing. A 3D render shows a flat, ring-shaped plate of iron and steel. The base is formed by stacking these annular plates into a thick, laminated cylinder. Heavy bolts, labeled bolts D, are driven through to clamp them together. This stacking method serves a critical electrical purpose, known as lamination. Solid iron blocks are vulnerable to Foucault currents, or eddy currents. These are loops of electrical current induced within conductors by a changing magnetic field, which circulate and waste energy as heat. Slicing the core into laminated plates restricts the path of these parasitic currents, preserving the magnetic energy for rotational force. We can now examine the inner circumference of this newly built laminated ring. 4 large primary magnetic poles, labeled long cores E, extrude inward toward the center. Tesla introduced asymmetry by adding 4 noticeably shorter intermediary cores, the short projections F, in the spaces between the main poles. This geometry allows Tesla to manipulate magnetic reluctance. Reluctance is the measure of a material's opposition to magnetic flux, similar to how a resistor opposes electrical current. The air gap between the long cores and the center is small, resulting in low reluctance. The short projections leave a much larger air gap, creating significantly higher reluctance. By varying the physical length of the metal cores, Tesla engineered a permanent, uneven distribution of magnetic flux throughout the motor's interior. Next, we must consider the electrical conductors that will magnetize these cores. The 4 long cores are wrapped tightly multiple times with standard copper wire to create the primary poles. The secondary poles use a distinctly different material. Here, the wire is cast from German silver or iron, using significantly fewer wrapping turns. German silver and iron possess much higher electrical resistance than copper. By reducing the number of turns on these short projections, Tesla also lowered their inductance compared to the densely wrapped copper coils. Modifying both the metallurgy and the number of loops allowed Tesla to tune the circuit's impedance without requiring external phase-shifting capacitors. We can now analyze how electricity behaves as it moves through these mismatched coils. This graph shows identical alternating current entering both circuits simultaneously. The timing of the current is dictated by the inductance to resistance, or L/R ratio. This ratio determines the speed at which current builds up in a magnetic coil. In the copper primary coils, the current wave establishes a baseline timing consistent with its specific ratio. In the secondary coils, the increased resistance and lower turn count change the ratio significantly, visibly shifting the wave to the right, lagging out of phase. This mismatch creates a functional phase difference, proving that mechanical geometry can dictate electrical timing. We now return to the fully wired physical model of the stator for its final component. Armature G, a solid cylindrical rotor, is placed perfectly within the central void of the stator. When the motor is energized, the first pulse of magnetic energy fires from the long cores and penetrates the armature. A fraction of a second later, the delayed current reaches the short projections, firing a secondary pulse in a staggered rhythm. This sequential pulsing forces the combined magnetic field to sweep in a circular motion around the inner circumference of the stator. This sweeping action exerts a continuous torque, dragging armature G into a smooth, relentless spin. These theoretical animations reflect the physical reality of Tesla's workbench in the late 19th century. Tesla's architecture functions as a highly tuned, spatial electromechanical filter. Modern variable frequency drives achieve these same phase shifts digitally, using microchips to time the pulses. However, Chapter 4 demonstrates that modern motor control foundations were first established through the manipulation of structural geometry and material science. Early alternating current systems suffered from a severe mechanical constraint. Without modern variable frequency drives, or VFDs, the speed of any motor connected to the grid was locked to the exact frequency of the power plant's generator. VFDs are electronic devices used to control motor speed by varying the frequency and voltage of the power supply. This one-to-one frequency lock created a bottleneck for industrial applications. A factory floor requires heavy lathes, textile looms, and conveyor belts to operate at distinct, independent speeds simultaneously. Modern engineers use silicon microprocessors to alter electrical frequency. In the late 19th century, variable control had to be achieved through mechanical architecture, the physical arrangement of heavy iron and copper. Nikola Tesla focused his research on breaking this frequency lock through physical design. His approach involved manipulating the spatial relationship of the iron and copper components within the machines to alter invisible electrical properties. Tesla's mechanical geometry enabled the AC motor to operate at various speeds, providing the adaptability required for industrial use. Chapter 6 of this 1894 compilation of his work serves as his foundational treatise on obtaining desired motor speeds from a fixed generator. The central thesis of the chapter relies on physical space. Motor speed can be controlled by manipulating the angular displacement of armatures and field magnets on a shared central shaft. We can see the variables of this theory in the heavy iron hardware of an early AC machine. Tesla used the mass and the specific physical layout of these components to alter the electrical phase differences of the system. A phase difference is the creation of multiple overlapping alternating currents that peak at different controlled times. For Tesla, generating an electrical phase shift was a spatial engineering challenge rather than a circuit problem. To control the speed of the motor, we must first go upstream to the generator to produce these out-of-phase currents. This diagram shows Tesla's most rudimentary configuration. Two complete machines are coupled by a rigid shaft, allowing an engineer to force an electrical phase difference by adjusting their alignment. While this method is clunky, it proves that a physical asset in the hardware generates an electrical phase shift in the current. He refined this into a compact configuration, fastening two separate armatures to a single shaft within a single magnetic field. By introducing a specific angular displacement between the two armatures, the phase difference is built into the rotating mass itself. A third configuration attaches two symmetrical armatures to the same shaft, but achieves the phase shift by displacing the stationary field magnets enclosing them. We now shift focus from the generator producing the phase to the motor receiving it. Phase-shifted currents create a rotating magnetic field inside the motor's stationary stator. These magnetic lines of force sweep in a continuous circle. This raises the core mechanical question: how does this fixed-frequency rotating field yield multiple distinct rotational speeds at the shaft? Tesla's key variable on the motor side is the specific ratio of magnetic poles wound into the motor's coils. The physical layout of these internal poles acts as a magnetic transmission system, stepping the mechanical speed up or down. By altering the number of poles, Tesla discovered how to geometrically multiply or divide the motor speed relative to the incoming electrical frequency. This comparative animation illustrates a motor wound to produce exactly 6 poles. The direct physical result is a 2-to-1 ratio. The 6-pole motor rotates twice as fast as the generator. The rotating magnetic field crosses more physical poles per cycle, pulling the rotor at a higher velocity. In a 4-pole configuration, for every generator rotation, the motor completes exactly 3. The motor rotates 3 times as fast. These integer multipliers provide predictable, solid operational speeds for industrial machinery. The rotational speed of the movable element is governed by this pole ratio. The magnetic design acts as a frictionless mechanical gearbox. Chapter 6 outlines one final mechanism: tuning speed via differential magnetic shifting. This model shows a scenario where the physical armature and the magnetic poles shift in the same direction. In this case, the final speed of the motor is not determined by the speed of the armature alone. Tesla's rule states that the final output speed is equal to the mathematical difference between the mechanical rotation rate and the magnetic shifting rate. This acts as a fine-tuning mechanism, allowing for precise speed adjustments without changing the primary generator's RPM. Differential shifting allowed engineers to define a motor's speed by the subtraction of physical rotation and magnetic energy. This created a complete system where a single generator could drive multiple motors at various custom speeds simultaneously. This mastery of alternating current scaled up to power the Industrial Revolution and was showcased to the world at the 1893 World's Columbian Exposition. Modern engineers use microprocessors and VFDs to manipulate frequency directly. Before the existence of solid-state electronics, this level of individual machine control was considered impossible on an alternating current grid. Tesla solved a frequency problem using spatial design and mechanical geometry. By hardwiring mathematical pole ratios directly into the machine's architecture, Tesla decoupled motor speed from the grid's fixed frequency, an engineering logic that still informs how we distribute power today. When we think of Nikola Tesla, we think of alternating current. But before he wired the world for AC, he engineered its rival, direct current. Arriving in America in the 1880s, Tesla entered a ruthless electrical market. To survive and secure patents, he needed to prove his technical competence immediately. At the time, the most lucrative commercial application for electricity was arc lighting. Cities and municipalities were paying top dollar to illuminate their streets and industrial factories. An arc lamp produces light by forcing a raw, high-voltage spark, or arc, to jump across a physical gap between two consumable carbon rods. To secure the capital and industry credibility required to pursue his alternating current theories, Tesla knew he first had to build a better DC arc light than his competitors. Tesla engineered this DC system explicitly to generate cash flow to fund his ultimate vision. He recognized that a reliable light required the generator and the lamp to function as a single, closed-loop system. The first half of the system was the power source, a direct current generator featuring a unique armature winding pattern. The second half was the load, an electromechanical lamp designed to physically regulate itself as it burned. Early arc lights were notoriously unstable. They sputtered and flickered, because the crude power output of the generators was poorly matched to the shifting electrical resistance of the burning carbon. By looking at Tesla's design from first principles, we can trace exactly how he solved this. We will start with the mathematics of his generator winding and follow the current to the mechanical clamp of the lamp. Treating power generation and power consumption as a coupled, interactive ecosystem allowed him to achieve a continuous beam of light. The primary challenge in designing a direct current generator is producing a smooth, continuous flow of electricity without causing destructive sparks at the commutator. The commutator is the rotating switch that collects the current from the generator. Tesla solved this sparking issue by inventing a highly systematic, segmented winding architecture for his armature, which carefully distributed the electrical load. This diagram illustrates his specific layout. The core utilizes exactly 24 coils, which connect directly to a 24-plate commutator ring. Instead of wrapping them randomly, Tesla split these coils into two overlapping layers. Here we see the first 12 coils forming the base layer. Within this layer, those 12 coils are mathematically divided into three specific groups, each containing exactly 4 coils. These specific groups are routed and soldered to their corresponding commutator bars in a sequence that optimizes the electrical phase, ensuring the voltage doesn't spike or drop erratically during rotation. Before adding the rest of the wire, this entire first layer is thoroughly insulated, creating a physical and electrical barrier. The remaining 12 coils are then grouped and wound directly over that insulated base, completing the dual-layer topology. By mathematically dividing the coils this way, Tesla mitigated rotational stress. The result was an exceptionally smooth, continuous current, the exact prerequisite for a steady arc. With smooth power flowing from the generator, that current travels directly to its destination, the arc lamp unit itself. This is the physical framework of Tesla's design. It is built on a sturdy base supported by parallel side columns to keep the moving parts aligned. The mechanical problem with any arc light is that the carbon electrodes vaporize as they burn. The widening gap eventually breaks the electrical arc. To prevent this, the lamp requires a regulatory brain. Tesla designed a mechanism using two opposing electromagnets to automatically adjust the distance between the rods. Looking at this schematic representation, the first component is the main magnet, or magnet M. It is wired directly in series with the arc, meaning the main electrical current flows straight through it. The second component is the shunt magnet, or magnet N. This one is wired in parallel to the main system, creating an alternate path for the electricity to flow. These two magnets sit above a tensioned spring and a pivoting lever. That lever controls a small clamp gripping the upper carbon rod. The architecture is built to translate invisible fluctuations in the magnetic field into precise corrective mechanical movements that continuously feed the carbon downward. Let's use this diagram to see the regulation cycle in motion. When the lamp first strikes an arc, the gap is optimal, the system is balanced, and current flows heavily through the main magnet. As the carbon slowly burns away, the physical gap widens. This physical change increases the electrical resistance of the arc. Because electricity always seeks the path of least resistance, the widening gap forces the current to divert. It flows away from the main magnet and surges into the parallel shunt magnet. This sudden influx of current strengthens the shunt magnet, causing it to exert a magnetic pull on the internal lever below it. As the gap continues to widen, the magnetic pull of the shunt magnet increases until it finally overcomes the physical tension of the calibrated spring. The lever shifts. As it moves, it slightly releases the grip of the mechanical clamp holding the upper carbon rod in place. With the clamp loosened, gravity simply pulls the newly freed carbon rod downward, instantly closing the widened gap. The moment the gap narrows, the electrical resistance drops. The current instantly rushes back to its preferred path through the main magnet. The re-energized main magnet overpowers the shunt. It pulls the lever back, snapping the clamp shut and locking the carbon rod in the perfect position. This continuous millisecond by millisecond feedback loop dynamically balanced the circuit, resulting in a perfectly stable, self-regulating, flicker-free light source. Zooming out, we see a closed-loop system where every component serves a specific interdependent function, from the spinning generator down to the burning arc. The unique 24-coil armature provided the flawless power delivery required for the dual magnet clamp to perform its delicate mechanical adjustments. The engineering worked. This reliable system successfully attracted the attention of early American investors and firmly established Tesla's reputation as an elite electrical engineer. By capturing a piece of the booming 19th century lighting market, Tesla secured the crucial financial runway needed to pursue his true passions. While his DC lamps lit the streets, Tesla was refining the alternating current theories that would eventually scale power distribution to a continental level. His foray into DC arc lighting was a rigorous end-to-end engineering foundation that directly funded the alternating current systems he would soon introduce to the world. When an industrial alternating current motor slams into motion, an invisible physical collision of magnetic fields is taking place. In the late 1880s, Nikola Tesla engineered the polyphase system. It uses multiple alternating currents to create a rotating magnetic field in the stationary outer part of the motor, the stator. Inside that stator sits the rotor, a distinct closed electrical circuit with its own mass and heavy iron core. As the stator's magnetic field sweeps around in a circle, it induces an electrical current within the rotor, forcing that iron core to spin. But there is a timing error in this physical interaction. The peak electrical current entering the stator does not immediately translate into peak magnetic force pulling on the rotor. Because of this mismatch, early alternating current motors fought their own internal physics. They were robbed of a significant portion of their theoretical mechanical power. The mechanical culprit is self-induction, the inherent resistance of an electromagnetic circuit to any change in the current flowing through it. Because the rotor contains a massive iron core and closed wire coils, its self-induction is high. When the stator applies a magnetic field, the rotor iron takes a fraction of a second to fully magnetize and react. This models the magnetic environment of a two-phase motor. A primary vector represents the stator flux sweeping around the center. A second vector emerges, showing the rotor's reaction visibly trailing behind. That gap is the literal angle of magnetic lag. Because of this gap, the maximum magnetic pull of the stator and the maximum reactive pull of the rotor occur at different spatial coordinates and at different moments in time. If those two magnetic peaks do not occur at the exact same instant, the motor is structurally prevented from achieving its maximum torque. The solution to this timing mismatch is documented in Chapter 17 of Tesla's collected writings. In a section detailing motors with coinciding maxima, Tesla outlines a specific engineering goal. To fix the delay in the rotor, the engineer must artificially retard the magnetic phase of the stator. Simply altering the timing of the incoming alternating current power source fails to solve the problem. The rotor's lag is a fixed physical property dictated by the mass of its iron and the gauge of its wire. Instead, Tesla altered the physical architecture of the motor. He divided the stator winding into multiple parallel electrical branches, rather than using one continuous coil. He maintained a primary path, which he called the main circuit, and ran secondary paths alongside it, known as the derived circuits. By altering the wire size and the number of turns in these derived circuits, Tesla deliberately manipulated their level of self-induction. He turned the physical construction of the stator into a customizable magnetic timing dial, allowing him to slow down the magnetic wave before it ever reached the rotor. Tesla's notes provide the exact mathematical configuration required to make this work. This phasor diagram models a standard electrical baseline, where two main stator circuits are separated by 30 degrees of electrical phase. When projected onto the physical poles of the motor, the magnetic flex lines skew, creating an uneven pole. Tesla replaced the standard coils with his tuned derived coils. The heightened self-induction acts as a localized brake, retarding the magnetic phase. It shifts backward by exactly 15 degrees, locking into place halfway between the original split. This 15-degree metric is the exact, unchangeable angle of magnetic lag generated by the rotor's iron core. Tesla mathematically delayed the stator's field to meet the rotor's lag halfway, perfectly splitting the difference in time and space. Returning to the physical model, we can finally observe the tuned stator and rotor interacting as a complete unified system. As the stator flux vector shifts backward, the angle of lag shrinks to zero, bringing both magnetic vectors into perfect alignment. The two magnetic peaks now pulse at their maximum magnitude together, hitting the exact same spatial coordinate at the exact same fraction of a second. Tesla termed this synchronized state maximum resultant attraction. By forcing the maxima to coincide, he eliminated internal magnetic fighting. The motor no longer wastes energy against its mismatched timing. This graph compares the raw mechanical output over time. The standard uncorrected motor generates a lower fluctuating torque, while the motor engineered for coinciding maxima produces a significantly higher optimized output. Maximizing electrical efficiency depends on the precise internal manipulation of inductance to synchronize invisible magnetic waves, the final proof of Tesla's mastery over alternating current physics. In the late 19th century, the earliest direct current dynamos had a habit of tearing themselves apart. The point of failure was almost always the commutator, where rapidly spinning carbon brushes transferred current and frequently erupted in destructive plasma blue arcs. These machines were built to drive commercial arc lighting systems. That required generating a massive electromotive force, or EMF. Switching that high-voltage direct current mechanically across spinning metal contacts proved highly volatile. Engineers at the time treated these sparks as a purely mechanical problem. The prevailing assumption was that imperfect brush materials, or simple friction, were scraping the metal away and generating excess heat. But polishing the commutators to a mirror finish or experimenting with lower friction alloys failed. Even the smoothest mechanical contacts could not stop the dynamos from literally melting their own components under load. The failure to solve this specific electromechanical problem prompted a young Nikola Tesla to examine the architecture of the direct current generator. Tesla realized the sparking had nothing to do with friction. The destruction was the result of electrical induction. To stop the dynamos from destroying themselves, he developed a two-part solution. First, he physically redesigned the geometry of the commutator's bearing surfaces. Second, he altered the topology of the circuit itself. He understood that preventing physical wear and tear required treating the machine's mechanical operation as a strict expression of electromagnetic laws. To see the mechanism of destruction, we slow the timeline down to the exact microsecond a carbon brush breaks physical contact with a commutator plate. The armature coils inside the dynamo are highly inductive components. Inductive components store energy in the form of a magnetic field as current flows through them. This chart shows the mathematical relationship defining that environment. Voltage equals inductance multiplied by the change in current over time. Faraday's law dictates an inductor will violently oppose any sudden change in current flow. That L variable acts as a kind of electrical inertia. When the mechanical brush snaps off the commutator plate, the physical circuit is broken almost instantly. Mathematically, our change in time, the denominator, shrinks rapidly toward zero. Dividing by a fraction approaching zero forces the output to scale exponentially. The resulting voltage vector spikes toward infinity. This massive voltage spike is known as back EMF. It is the inductor's collapsing magnetic field desperately attempting to keep the current flowing across the newly formed physical void. The voltage becomes so high that it breaches the dielectric strength of the surrounding air gap. Dielectric strength is the maximum electric field a material can withstand before losing its insulating properties. Once that threshold is crossed, the back EMF ionizes the air itself, bridging the gap with a destructive plasma arc that vaporizes microscopic layers of the metal commutator. The spark is not a design flaw. It is the strict mathematical penalty for forcing an instantaneous current break in an inductive system. Tesla's initial method for mitigating this penalty involved reshaping the physical architecture of the commutator itself to manipulate the physical timeline of the break. The standard geometry of early commutators relied on flat bearing surfaces oriented parallel to the shaft. This layout caused the brush to drop off the edge abruptly, creating a near-instantaneous disconnect. This chart shows how Tesla modified the design. He took the bearing surfaces and oriented them at right angles to the rotational shaft. This specific geometric orientation optimized the total surface area available for electrical contact between the brush and the commutator plates. By angling the surface, the physical alteration subtly stretched out the micro-timing of the mechanical disconnect. The brush tapered off its contact gradually, which fractionally increased the change in time in our earlier equation. Geometry has strict limits. Even with right angles easing the transition, the physical break eventually occurs. The inductive kickback is delayed and reduced, but not entirely eliminated. Reshaping the metal was only half the solution. To safely dissipate the remaining energy, the current required an alternative topological escape route. Tesla's ultimate solution was a topological circuit intervention known as the auxiliary brush. This diagram shows the physical placement of the new system. It consists of the primary main brush and an offset secondary auxiliary brush, wired in parallel. During normal operation, the high-voltage direct current flows continuously and stably straight through the main primary brush. But look at the exact microsecond the main brush breaks its physical contact with the rotating segment. Because of its offset position, the auxiliary brush maintains a closed secondary circuit for a fraction of a second after the main break occurs. Instead of meeting an air gap and ionizing the oxygen at the main brush, the inductive kickback eagerly takes the path of least resistance, flowing directly through the closed auxiliary circuit. This parallel routing safely bleeds off the high-voltage transient energy, entirely bypassing the air gap and operating without generating a single spark at the primary terminal. Tesla did not defeat Faraday's law. He simply built a mechanical pressure relief valve that allowed the physics to resolve safely elsewhere. The contrast in results was stark. Standard single-brush dynamos degraded violently under their own electrical loads, while Tesla's dual-brush topology allowed for silent, sustainable operation. Mastering the stability of these high EMF dynamos enabled the massive scale of early commercial power distribution, paving the way for the vast electrical pavilions at the World's Fair. The underlying engineering philosophy proved that parasitic electrical transients cannot be blocked by brute force. They must be topologically redirected. This intense study of microsecond circuit breaks also set the foundation for the next phase of Tesla's career. The exact phenomenon he worked so hard to suppress here, the inductive kickback of a sudden break, became the precise mechanism he would seek to maximize. Isolating and amplifying these violent inductive spikes led directly to his later investigations into high-frequency, high-potential disruptive discharges. Tesla's engineering extended beyond repairing early generators. He realized that the parasitic anomalies destroying these dynamos provided the foundation for an entirely new branch of physics. Ohm and Kirchhoff's laws dictate a strict rule for classical electrical engineering. Power requires a closed loop. Current cannot flow without a continuous return path to its source. Yet, if you hold this glass vacuum bulb attached to a single wire, it illuminates. According to standard circuit mechanics, this is impossible. Conventional ohmic heating requires a continuous flow of electrons passing through a resistor and returning to the generator. Here, the circuit simply stops at the glass. In 1891, cities were only just being wired for electricity. The existing infrastructure relied entirely on low-frequency, closed-loop systems, primarily using direct current. On May 20th of that year, Nikola Tesla addressed the American Institute of Electrical Engineers. Standing before his peers at Columbia College, he presented a series of experiments that defied the established physics of the day. By accelerating alternating currents to extreme high frequencies, Tesla demonstrated that the actual physical mechanism of generating light shifts entirely. To understand how a single wire can light a bulb, we have to discard the classical plumbing model of electricity, where electrons flow through pipes, and examine the dynamics of radiating electrostatic fields. Here is the structural difference. The standard left design produces light through ohmic heating, forcing electrons through a continuous loop until it glows. Tesla's right design abandons the filament entirely. Energy radiates outward from a single wire's central button directly into space. As you increase the frequency of an alternating current, the physical effects change. The audible acoustic vibrations, like the hum of a standard alternating arc, gradually become shriller, weaken, and eventually cease as human hearing fails us. When alternations breach tens of thousands of cycles per second, new forces govern the system. At these extremes, induction phenomena dictate the current's behavior. The electrical current traveling through the wire is no longer the primary physical actor. The rapidly alternating electrostatic field takes over, making the closed-loop wire filament obsolete. Looking at a cross-section of the interior of Tesla's highly exhausted vacuum tube, we see the central button surrounded by a sparse population of gas molecules. Even the best vacuums were not perfectly empty. As the electrostatic field rapidly reverses polarity, floating gas molecules violently jerk back and forth. Driven relentlessly against the central terminal at staggering speeds, millions of kinetic impacts generate a brilliant, blinding white light. Most materials would disintegrate under this assault. To survive the bombardment, Tesla engineered a highly refractory terminal button made of carborundum. He manufactured these by mixing a thick paint of carborundum and tar, coating a wire, and baking it over a hot plate until the tar evaporated, leaving a solid, impact-resistant coating. The illumination is not electrical friction inside a continuous wire. It is the result of microscopic kinetic collisions orchestrated by a high-frequency field. The initial paradox remains: without a second return wire, how does the system maintain electrical equilibrium? We have to look at the source of the power. Tesla generated these effects using specialized high-frequency alternating generators and disruptive discharge coils, reaching immense potentials. This diagram shows capacitive coupling. The hand holding the glass and the ambient air act as a capacitor's second plate, drawing energy outward. The physical evidence is the brush discharge phenomenon, where luminous streams of energy radiate from the wire directly into the surrounding space. Tesla observed that at proper frequencies, this discharge streams abundantly from the whole surface of the conductor, resembling a high-pressure jet of escaping gas. The single-wire bulb is not an open circuit. At extreme frequencies and potentials, the surrounding medium itself seamlessly completes the loop. Zooming out from the microscopic collisions, the apparatus operates as a unified, radiating field of energy. Tesla achieved luminosity by using 5-frequency fields to trigger atomic impacts. This bypassed the standard method of forcing current through resistive filaments. This led to an efficiency paradox. The molecular bombardment produces an intense, vivid light, yet the system operates at a comparatively very low mean temperature. Traditional incandescent bulbs waste massive amounts of their input energy as heat. Tesla's high-frequency approach targets the emission of light directly. With these demonstrations, his 1891 lecture fractured the strict boundaries of 19th-century electrical theory, proving that the rigid rules of direct current did not apply at high frequencies. His empirical observations of gas phosphorescence and molecular bombardment laid the groundwork for modern plasma physics, neon lighting, and fluorescent tubes. By proving that energy could couple seamlessly with the surrounding medium, Tesla's single-wire bulb established the functional proof of concept for the wireless electromagnetic era. To transmit electrical power and perform actual work, electrons require a continuous, closed conductive loop, a physical circuit where the current flows out from a source and returns to it. On February 3, 1892, Nikola Tesla stood before the Institution of Electrical Engineers in London and directly challenged that strict electromagnetic requirement. He presented the audience with an evacuated glass bulb containing a refractory button. He then connected this bulb to a high-tension terminal using only a single wire. Despite having absolutely no return wire to complete the circuit, the refractory button inside the bulb glowed brilliantly when power was applied. The demonstration proved that at extreme limits, the physical requirements for power transmission change. Standard electrical engineering operates at relatively low frequencies and potentials. At these levels, the system relies on closed-loop electromagnetic dynamics, acting like a fluid pipeline pumping electrons through a physical medium. Tesla scaled alternating current frequencies and voltage potentials to their absolute upper physical limits, reaching tens of thousands of volts, oscillating millions of times per second. At these levels, the electrical system behaves less like a fluid pipeline for electrons and more like an acoustic resonator. In this resonant state, electrostatic forces overtake standard electromagnetism as the dominant mechanism for performing physical work. To understand how transferring energy without a closed loop is possible, we must reverse engineer the circuit architecture Tesla used in 1892 to induce this transition into electrostatic dominance. This schematic illustrates the topology of Tesla's impedance experiment. He set up a thick, highly conductive U-shaped copper bar and shunted the two legs of the U with standard incandescent lamps. When a standard low-frequency current is applied to the system, the electrons take the path of least ohmic resistance. Here, that path is the thick copper bar. Because the delicate filaments inside the incandescent lamps possess a much higher physical resistance than the heavy copper, the electricity bypasses them entirely, leaving the lamps dark. The results change when the power supply is switched to a rapidly alternating high-frequency current. This introduces self-induction, a property where rapidly expanding and collapsing magnetic fields create an opposing force within the conductor, choking the flow of electrons. The U-shaped bar, which offers the least ohmic resistance, has now become the path of highest inductive resistance. The impedance generated within the copper physically blocks the high-frequency current. Seeking relief, the current bridges the gap, routing through the high-resistance filaments and illuminating the lamps. High-frequency impedance allows engineers to route electrical power using inductive fields rather than relying exclusively on physical copper pathways and insulators. Generating the frequencies required for this experiment presented a severe problem. Standard 19th-century mechanical alternators could not spin fast enough to produce them. This diagram outlines the first stage of Tesla's solution. He used a step-up transformer to convert low-frequency AC into very high-voltage AC. A step-up transformer is a device that increases voltage while decreases current through electromagnetic induction between two coils. He then fed this high-voltage AC into a condenser. A condenser, or capacitor, is an electrical component designed to store and release an electrical charge. The circuit was then interrupted by a spark gap. This gap acts as an electrical pressure valve, holding the charge back until a specific voltage threshold is reached, at which point the electricity forces its way across. When the spark jumps that gap, the condenser does not discharge its energy as a single pulse. Instead, it discharges as a heavily damped, ultra-rapid oscillation. Routing these rapid oscillations through a final primary coil completes the disruptive discharge circuit. This architecture translated standard low-frequency power into the high-frequency electrostatic engine required to manipulate alternating fields. This electrostatic engine explains the single-wire motor demonstration from the London lecture. The setup featured a primary coil connected to only one terminal of the high-frequency generator. Placed next to it was a closed secondary coil and a freely movable metal disc. Under standard physics, this motor cannot operate because there is no return wire connecting the primary coil back to the generator. The motor is driven by stray capacitance, a phenomenon where electrical charge bleeds into surrounding materials. At these extreme frequencies, stray capacitance allows the single wire to interact with the ambient environment. Because the alternating electrostatic field oscillates so rapidly, it uses the surrounding air, the dielectric, as a temporary storage reservoir for the charge. The dielectric is the insulating material that supports an electrostatic field, even if it does not conduct electrons. The circuit is technically closed. The extreme frequencies have simply moved the return path from a physical copper wire into the room itself. Tesla's practical goal for the 1892 lecture was the creation of a highly efficient light source that completely eliminated resistive filaments. He constructed a glass bulb containing a single button of refractory material, a substance resistant to high heat, mounted on a central wire. When the high-frequency electrostatic field is applied to that wire, the few gas molecules remaining inside the vacuum are repelled and attracted by the alternating charge. These oscillating molecules act as microscopic hammers, violently colliding with the central refractory button millions of times per second. The kinetic energy of these microscopic impacts generates intense heat, bringing the solid button to brilliant incandescence. Electrostatic fields can translate electrical energy into heat and light through kinetic bombardment, removing the need to push current through a resistive filament. Every demonstration in the 1892 London lecture, from the impedance of the copper bar to the molecular bombardment inside the vacuum bulbs, pointed to a single conclusion. A physical transmission wire is not an absolute requirement for power to flow. It is a guide for the energy. At sufficient frequencies and voltage potentials, the electrostatic field itself replaces the copper wire as the mechanism for performing work across a distance. By deconstructing the necessity of the closed conductive loop, Tesla laid the demonstrable foundation for the wireless transmission of power. In the late 19th century, alternating current grids spread rapidly across cities. Engineers could easily step up AC voltage to transmit power over vast distances with minimal loss. But at the end of the line, taking high voltage power and converting it into heavy mechanical work presented a massive physical hurdle. Despite the transmission efficiency of AC, heavy industry remained tethered to direct current systems and the massive physical infrastructure required to get work done. Getting a factory floor moving from a dead stop required immense rotational force. These networks of belts, pulleys, and overhead shafts carried extreme physical resistance, demanding an electric motor that could generate massive starting torque. This created an engineering bottleneck. Alternating current was perfect for pushing power through miles of wire, but early AC motors were weak at generating the initial torque needed to move dead weight without relying on complex, spark-prone mechanical commutators. Nikola Tesla focused his research entirely on solving this specific bottleneck. He saw that polyphase alternating currents contained the mathematical properties needed to generate rotational force without mechanical switches. The factory floor demanded a strict dual mandate. A motor had to deliver the brute starting torque to move heavy loads, and then, once running, it had to lock into a precise, unwavering speed to maintain delicate manufacturing processes. In the 1880s, these two requirements were considered mutually exclusive. High starting torque and locked speed precision were viewed as contradictory engineering problems requiring entirely different types of machinery. To master alternating current, an engineer had to design a single machine capable of delivering both, solving a physics paradox electricians thought was mechanically impossible. The ideal solution for steady operation is a synchronous motor. A synchronous motor is a machine where the inner rotor matches the electrical frequency of the power grid, locking its rotation to the alternating current so it maintains constant speed regardless of load. This perfect synchronization is exactly what factories need. It ensures that looms, lathes, and assembly lines operate with absolute timing and consistent output, hour after hour. But the purely synchronous design has an inherent limitation at startup. When the power switch is on, the outer magnetic field instantly rotates at full speed, but the heavy inner rotor is still at 0 RPM. The magnetic forces rapidly push and pull in opposite directions, canceling each other out and leaving the rotor vibrating in place. Because of this alternating cancellation, a purely synchronous motor cannot start itself. It requires an external mechanical force, like a separate starter motor, to spin it up to the grid's electrical frequency before the magnetic fields can lock together. Tesla eliminated the need for an external starter. His 1894 collected writings include a specific section detailing his solution. Chapter 11, titled Another Method of Transformation from a Torque to a Synchronizing Motor. Tesla designed a machine that starts with high torque and then transitions through distinct operating states mid-flight to become synchronous. To understand how this motor operates, we have to look inside the casing and break down how a machine alters its mechanical behavior using nothing but invisible magnetic fields. The bedrock of Tesla's phase-shifting architecture is the rotating magnetic field. By feeding alternating currents into the stationary outer ring of the motor, called the stator, he created a magnetic field that continuously rotates around the center of the machine. To generate starting rotational force, or torque, This invisible stator field must move significantly faster than the physical rotor resting inside it. This creates a specific condition called slip. Slip is the difference in rotational speed between the fast-moving stator field and the slower rotor mass. Because of this, the stator's magnetic flux lines rapidly intersect the stationary metal bars of the inner rotor. This intersection triggers Faraday's law of induction. Faraday's law dictates that a moving magnetic field intersecting a conductor induces a voltage across it. This action forces an electric current to flow through the metal of the rotor. Once current flows through the rotor bars, the rotor generates its own secondary magnetic field, pushing out against the stator. The interaction between these two competing fields generates the Lorentz force. The Lorentz force is the electromagnetic push exerted on a current-carrying wire in a magnetic field, and here it creates the massive torque necessary to shove the heavy rotor into motion. The motor's ability to start moving relies entirely on its initial failure to keep up. It utilizes the slip of this asynchronous state to harvest power needed to rotate the shaft. As the starting torque overcomes inertia, the physical rotor begins to accelerate, chasing the rotating magnetic field that is pulling it forward. This graph tracks slip against power. As rotor speed increases, slip decreases, dropping the induced torque curve. Why? The faster the rotor spins, the closer it matches the stator field. The relative speed shrinks, cutting fewer flux lines, which weakens the induction. This reveals the inherent limitation of a pure induction motor. It cannot reach perfect synchronous speed, or zero slip, on its own. If the rotor ever perfectly matched the stator field's speed, there would be no relative motion. No lines would be cut, induction would stop entirely, torque would drop to zero, and the mechanical load would immediately force the motor to slow down again. This creates a perpetual gap. The motor reaches a cruising speed just marginally below the rotating field, held balanced by the physical resistance of the load it is pulling. At this near-synchronous cruising speed, the standard induction motor is trapped. It will plateau in this asynchronous state. Closing that final gap and achieving strict synchronization requires a hidden mechanism. Tesla solved this by modifying the rotor with specific magnetic properties. By shaping the iron core with distinct salient poles, or embedding that direct current-excited circuit, he created permanent magnetic focal points within the spinning mass. These focal points remain dormant during the heavy lifting of the startup phase. As the rotor's momentum carries it close to the speed of the rotating stator field, the magnetic forces shift. Once the gap is narrow enough, direct magnetic attraction overcomes the final fraction of slip. The rotor is pulled forward into rigidly locked rotation. The immediate mathematical consequence of this physical snap is that slip instantly drops to absolute zero. Because the rotor and the magnetic field are now traveling at the exact same velocity, the flux lines stop cutting across the metal bars entirely. Without that intersection, the induced alternating currents inside the rotor cease. The machine goes electromagnetically quiet. The motor is no longer driven by the induced currents of Faraday's law. Instead, the load is pulled entirely by direct static magnetic attraction between the inner and outer fields. The Chapter 11 transition is complete. The machine has moved from an induction-based start to a perfectly locked synchronous rotation. By executing this transition entirely through electromagnetic fields, Tesla bypassed the severe limitations of contemporary engineering. Older direct current machines and early attempts at alternating current motors relied heavily on physical brushes and cylindrical commutators to manually switch the direction of the current and keep the shaft spinning. On a heavy industrial factory floor, this mechanical switching was a fatal vulnerability. Constant physical contact at high speeds generates intense friction, sparking, excess heat, and eventual mechanical failure. The elegance of Tesla's design lies in subtraction. He completely removed the physical, moving switch from the equation. The mechanical switching was replaced entirely by the geometry of the alternating currents themselves. As the current naturally pulses back and forth, the magnetic fields rotate perfectly in step, meaning one electrical cycle equals exactly one mechanical rotation. This dual-action architecture allowed alternating current to conquer the factory floor. It provided the immense starting torque required to move tons of iron and the precise timing necessary for manufacturing, all with minimal physical degradation over time. Tesla built a physical system that transitions through distinct magnetic states to match the shifting needs of the industrial grid. By bridging the gap between heavy starting torque and locked speed precision, he aligned. To understand the mechanical flaws of early alternating current motors, we must examine the rotating inner core, the armature. This armature is not a solid block of metal. It is constructed from a massive, continuous spool of conductive copper wire wound tightly around an iron core. Because of this specific geometry, the entire physical structure behaves electrically as a massive inductor. An inductor is a passive electrical component that stores energy in a magnetic field when electric current flows through it. The defining physical trait of any inductor is its strict opposition to change. If you attempt to alter the rate of current flowing through the wire, the inductor's magnetic field pushes back against that change. When we apply an alternating current, a signal that reverses directions dozens of times per second, this resistance is continuous. The coil constantly fights the oscillating current, creating a phenomenon known as self-induction. As the voltage pushes forward, the self-induction forces the actual current wave to physically lag behind the voltage wave in time. This inherent delay cripples the motor. The lag prevents efficient power transfer from the stator to the armature, suffocating the mechanical output of the machine. Nikola Tesla approached this mechanical deficit by altering the internal circuitry of the motor itself. In Chapter 21 of his collected writings, Tesla details a highly specific topological intervention. He placed a condenser directly in series with the rotating armature circuit. A condenser, referred to in modern engineering as a capacitor, is a passive component that stores electrical energy in an electrostatic field. Tesla stated his rationale clearly. Resort is had to condensers for the purpose of developing the required difference of phase and neutralizing the effects of self-induction. The first objective outlined in that text is strictly corrective. Tesla aims to neutralize the inductive reactance, eliminating the electrical lag suffocating the armature. The second objective is generative. He intends to force an artificial phase difference between the motor's magnetic fields to maximize rotational torque. Tesla is addressing a physical rotation failure through a purely solid-state electrical modification, bypassing the need for complex mechanical redesigns. To see exactly how a stationary capacitor fixes a rotating machine, we have to map the physical forces into a mathematical model. This diagram shows a standard 2D coordinate plane, allowing us to build a phasor diagram. A phasor diagram is a graphical tool used by electrical engineers to map the magnitude and timing of alternating currents and voltages. We plot the system's baseline voltage as our reference vector, extending horizontally along the x-axis. Because the massive coils of the armature act as an inductor, the resulting current vector does not align with the voltage. Instead, it drops downward by exactly 90 degrees. This 90-degree angular gap is the phase lag, caused entirely by inductive reactance. Inductive reactance is the specific opposition that a coil offers to an alternating current, measured mathematically in ohms. This exact visual separation between the voltage and current vectors is the mathematical representation of the inefficiency paralyzing the physical motor. This angular gap directly controls the system's power factor, a critical metric of electrical efficiency. The governing equation for AC power dictates that real power equals voltage multiplied by current multiplied by the cosine of the phase angle between them. As the phase angle widens toward 90 degrees, the cosine of that angle mathematically approaches zero. Multiply any voltage and current by zero, and your usable output drops to zero. The circuit is flooded with high voltage and high current, yet it yields almost zero mechanical work. Inside the physical motor, this trapped electrical energy has to go somewhere. It dissipates into the iron core as excess heat, leaving the rotor with sluggish, unusable rotation. Unless the engineer can artificially force that phase angle closed, the motor will perpetually consume massive amounts of grid power without generating the rotational force required for industrial use. This is exactly where the condenser intervenes, acting as the mathematical mirror image of the inductor. While an inductor forces current to lag behind voltage, a purely capacitive circuit dictates that current mathematically leads the voltage by exactly 90 degrees. This diagram now plots the new capacitive force onto our established model, creating a vector that points strictly upward along the positive y-axis. This upward force is capacitive reactance, the specific opposition a capacitor offers to alternating current. We now have two directly opposing forces locked on the same mathematical axis. The armature's natural inductance pulls straight down, while the newly inserted condenser pulls straight up. The capacitor does not physically push the rotor. It acts as an invisible electrical counterweight within the circuit itself. By introducing this specific capacitive force, Tesla deployed a targeted mathematical weapon designed solely to fight and cancel the armature's inherent downward lag. Analytical. The engineering solution requires sizing the condenser's capacitance to perfectly match the armature's heavy inductance. This animation shows the vector math in action. When these two opposing values are equal, the upward capacitive vector physically subtracts from the downward inductive vector, shortening the downward pull until it reaches zero. With the downward pull erased, the main current vector is freed. It swings upward, entirely closing the phase angle, and realigns perfectly parallel with the voltage vector. This exact state of alignment is called electrical resonance. In a state of resonance, the circuit's overall reactance drops to zero. Maximum current can now flow completely unobstructed through the massive coils of the armature, moving perfectly in sync with the voltage. Tesla successfully executed the first half of his thesis. He mathematically neutralized the effects of self-induction, restoring the motor's power factor to a perfect 1. This schematic illustrates how this tuned electrical circuit translates back into physical mechanics. We trace the alternating current as it passes through the condenser and directly into the armature coil. Eliminating electrical lag restores mathematical efficiency and grants the operator precise control over the armature's magnetic pulse. Continuous polyphase motion requires that the armature's magnetic field forms and interacts at a highly specific, staggered spatial angle relative to the stationary field coils. By intentionally over-tuning or under-tuning the condenser, an engineer can artificially shift the current phase, actively dialing in the exact magnetic interaction angle required between the two fields. This achieves the second half of Tesla's design, using a passive component to actively force the required difference of phase, generating continuous, reliable mechanical torque. Tesla's topological intervention executes two highly distinct physical functions simultaneously. First, the condenser operates as a power factor corrector. It rescues electrical energy that would otherwise be lost as heat by neutralizing the heavy induction of the copper coils. Second, it operates as a phase shifter. It establishes and controls the precise magnetic timing conditions required to force a heavy iron rotor to spin. He solved the dynamic, moving problem of rotational torque using an entirely stationary, solid-state component without moving parts. This specific physical configuration proved that abstract vector mathematics could dictate the output of heavy industrial hardware. Tesla isolated the armature's greatest inherent flaw, its massive, suffocating self-induction, and manipulated it into a highly tuned, resonant circuit capable of driving the alternating current motor. The core engineering constraint of the late 19th century electrical grid was a matter of material science. Solid-state diodes did not exist. A diode is a one-way electrical valve that seamlessly converts alternating current, AC, into direct current, DC. Without these simple solid-state valves, stepping down or converting power mid-circuit became a massive infrastructure hurdle. The industry faced a strict contradiction. Long-distance transmission required high-voltage AC to minimize energy loss, but the translating devices at the destination, like electrolytic meters and early arc lamps, demanded steady DC power. Grid architects had to find a way to extract the unidirectional flow out of the alternating wave exactly where the consumer needed it, without bleeding off the transmitted energy. A solution exists in the historical record, documented by Nikola Tesla during the height of the War of the Currents. In his collected writings, specifically Chapter 33, titled Method of Obtaining Direct from Alternating Currents, Tesla outlines a topological workaround. He designed a stationary electromagnetic network that extracted continuous direct current directly from an alternating line, completely bypassing the need for semiconductor materials. By arranging wire, iron, and magnetic fields into specific geometries, he achieved the exact results of a modern solid-state diode using purely macroscopic physics. To understand why a stationary rectifier was necessary, we have to look at the era's standard, brute force workaround for AC to DC conversion, the mechanical commutator. This device relies on split brass rings and carbon brushes to physically break and flip the circuit connections in time with the alternating wave. Because they required physical motion, these commutators had to be mounted directly onto the spinning shafts of the central power dynamos. This design introduces severe kinetic limitations. The constant physical friction degrades the carbon brushes over time. Electrically, as voltages scale up, the physical air gaps between the spinning rings and brushes trigger violent, destructive arcing. Plant operators were forced into a cycle of severe maintenance overhead, continuously replacing burnt brushes and resurfacing pitted metal components. Engineers urgently sought a way to separate the act of rectification from the kinetic generation of power. The industry's holy grail was a stationary device with zero moving parts that could sit mid-circuit, miles away from the generator, and quietly output DC. Escaping this mechanical, kinetic bottleneck was the strict prerequisite for scaling the electrical grid across continents. This diagram outlines Tesla's baseline circuit topology. Generator A acts as the primary source, producing a standard alternating current. That current travels down the main transmission line, labeled B, carrying a full symmetrical AC waveform. Here, Tesla's architecture diverges. He splits the single line B into two parallel branches. These new branches, labeled C and D, form distinct, isolated pathways for the divided electrical flow. He then places his translating devices, the DC loads, labeled here as O, directly within these specific branches. The problem with this topology is symmetry. An unaltered AC wave will split equally, subjecting the loads in both branches to alternating current. Parallel wiring alone fails to rectify. Without an asymmetrical filter to block half of the incoming wave, the translating devices receive a net DC power of 0. Tesla solves this symmetry by inserting active electromagnetic devices directly into branches C and D. He applies localized magnetic fields to create what he calls active opposition against the current flow. As the moving charge of the AC wave meets the magnetic field, an interaction occurs. The alternating current hitting the magnetic field induces a reverse electromotive force, known as back EMF.
Back EMF is a voltage that pushes against the current which induced it. This behavior is governed by Lenz's law, a principle stating that an induced current will flow in a direction that opposes the change that produced it. The back EMF will actively resist the incoming wave's change in current. The engineering trick here is asymmetry. Tesla aligned the magnetic fields in opposite directions across the two branches. This specific alignment suppresses the negative half-cycle of the wave in branch C, while simultaneously suppressing the positive half-cycle in branch D. By weaponizing Faraday's laws of induction, Tesla created a stationary one-way current valve decades before the discovery of semiconductor physics. Tesla did not rely strictly on pure induction. Chapter 33 also documents mechanical sub-circuit alternatives to prove the underlying principle. This schematic shows a rotary commutator placed directly across the split branches, physically isolated from the main generator. In this configuration, the commutator acts purely as a mid-circuit switch, completely detached from the kinetic generation of the power itself. But this method introduces a strict operational constraint, explicitly outlined in his text: perfect rotational synchronism. The commutator's rotation must mathematically lock to the exact frequency of the incoming AC alternations. As it spins, it physically diverts the positive waves into branch C and the negative waves into branch D in real time. Maintaining perfect mechanical synchronism in 19th century systems, which lacked modern digital feedback loops, was incredibly difficult. Whether utilizing active magnetic opposition or synchronous mechanical switching, the underlying engineering principle remains identical: phase-locked waveform diversion. Modern electrical engineering expect direct current to look like a perfectly flat line with zero ripple. The reality of the physics is that Tesla's active magnetic opposition does not yield perfect continuous DC. This chart shows the result of mathematically subtracting the induced back EMF from the source AC wave.
The resulting calculated waveform is highly asymmetrical rather than perfectly clipped. A small negative dip survives the magnetic suppression during every cycle. Tesla recognized this. In his text, he refers to the massive positive area of the waveform as the preponderating wave. He writes that whether the division of the currents is affected with absolute precision or not is immaterial to the final result. A massive mathematical asymmetry pushes so much energy in a single direction that it becomes functionally identical to pure direct current. This diagram compares the modern idealized approach to rectification against Tesla's pragmatic 19th century reality. The final variable is the translating devices. In the 1890s, these were electrolytic meters or early arc lamps. Their physical thermal inertia automatically smooths out the pulsating ripple of the preponderating wave. The device simply absorbs the net forward energy. Rectification was achieved through pure circuit topology and applied geometry rather than through material science. We solve this exact same problem today by relying on the chemical doping of silicon and the microscopic manipulation of semiconductor band gaps. The overarching engineering philosophy here is that satisfying the practical physical conditions of the load is often superior to chasing unnecessary mathematical perfection. This stationary rectifying topology bridged the vital gap between the high efficiency of alternating current long-distance transmission and the strict requirements of localized direct current utilization. Tesla solved the era's greatest power distribution bottleneck. He weaponized the very inductance that defines alternating current to tame and direct it.
Alternating current constantly reverses direction 50 to 60 times a second. Yet to do useful work, a motor must convert this into continuous unidirectional rotation. The modern AC induction motor solves this by discarding mechanical brushes entirely. Instead, it relies on a rotating magnetic field, a continuous magnetic wave that sweeps in a circle, dragging the motor's heavy iron rotor along with it. This diagram shows the electrical requirement needed to generate that rotating field, polyphase power. Here, two distinct alternating currents, represented by the two sine waves, flow into the motor's stator. Notice the horizontal gap between the peaks of the two waves. That offset timing, a built-in phase difference between current A and current B, is what physically pushes the resulting magnetic vector from one set of coils to the next, creating a smooth, sweeping circle. While mechanically elegant, polyphase power requires generating stations to produce, and cities to wire, multiple parallel transmission lines to deliver those offset currents to a single machine. True polyphase power is highly efficient for heavy industry, but logistically complex and prohibitively expensive to distribute to every individual user on the grid. This creates an immediate engineering constraint. What happens if a user only has access to a single phase line, just one wire pair delivering one alternating current? If you remove that second phase, the physics inside the motor change entirely. The rotating vector in the stator collapses into a single straight line, pulsing straight up and down in time with the lone sine wave. A pulsating field produces zero starting mechanical torque. Because the magnetic force pushes dead center on the rotor's axis, it cannot decide whether to push left or right. Caught in this top dead center stall condition, the motor simply sits there, shuddering and overheating, until someone physically spins the shaft to provide a directional bias. Nikola Tesla recognized this limitation and set out to run a self-starting motor on a single phase, eliminating the need for massive grid upgrades. To get rotational torque, physics demands two electrical phases, but the infrastructure often provides only one. The definitive record of his solution is documented in the 1894 volume edited by Thomas Commerford Martin, The Inventions, Researches, and Writings of Nikola Tesla. Within this extensive archive of early electrical engineering, one specific section addresses the single-phase paradox directly. Chapter 13 outlines a method for operating motors from a single alternating current by obtaining a difference of phase through magnetic shielding. Tesla's architecture routes the exact same single-phase electrical current into two different sets of magnetic poles inside the motor simultaneously. Because the electricity arrives at both sets of poles at the exact same instant, the internal geometry of the motor itself must physically delay the manifestation of the magnetism. This diagram shows Tesla's physical intervention. He added a closed metal loop, a magnetic shield, around the vertical poles, set A. The horizontal poles, set B,
remain standard coils. When single-phase current flows in, set B's magnetic flux grows in perfect synchronization. The shielded poles of set A, however, are governed by Lenz's law. Lenz's law is a principle of electromagnetism, stating that an induced current will always flow in a direction that opposes the change in the magnetic field that produced it. As primary alternating current pushes a changing magnetic field through the iron pole, it induces a secondary current inside the thick metal shield. This secondary current generates its own magnetic field, strictly opposing the main magnetic flux trying to pass through it. The main magnetic flux ultimately overpowers the shield's resistance and builds to full strength. But this electromagnetic struggle significantly slows its progression through the iron. The shield acts as an electromagnetic brake. It does not permanently stop the magnetic field. It alters exactly when that field reaches its maximum strength. This graph compares the two pole sets. Top, unshielded set B perfectly matches the electrical wave. Bottom, shielded set A is shifted right, peaking later. Measuring the gap between these peaks confirms a single electrical phase is effectively split into two distinct magnetic phases. This measured delay aligns exactly with the mechanics Tesla outlined in his 1894 patent specifications. He wrote that the shield ensures the manifestation of the free magnetism in poles A is so delayed beyond the period of maximum magnetic effect in poles B. Tesla translated a temporal problem, the lack of a second wave of electricity, into a spatial solution by altering the physical path the magnetism must travel. Observing the full motor system, the new magnetic delay is active. Set B pulses, followed milliseconds later by set A, drawing a continuous sweeping circle. This rotating vector grips the rotor, forcing it into a continuous spin and bypassing the stall condition. This mechanical reality directly supports Tesla's concluding claim for this architecture. He concluded that, quote, a strong torque is produced and the motor operates with approximately the power developed in a motor energized by independently generated currents differing by a full quarter phase. The motor successfully synthesizes polyphase power internally, generating enough rotational torque to perform heavy mechanical work while drawing from a single-phase grid. These vector theories were rapidly translated into physical hardware. This technology allowed AC motors to be deployed immediately, without waiting for the massive infrastructure upgrades required to wire the world for polyphase industrial power. Modern engineers rely on direct descendants of this principle. Shaded pole motors use highly conductive copper rings to delay magnetic flux, providing the starting torque for millions of household fans and appliances today. Chapter 13 outlined an elegant abstraction, taking the concept of phase from the distant power plant and embedding it directly into the machine's geometry. Tesla demonstrated that the boundaries between electrical supply and magnetic architecture are fluid, proving that precise physical design can synthesize the forces required for motion.
Alternating current is exactly what it sounds like. Electrical energy sloshes back and forth inside a wire, constantly reversing its flow, which makes it difficult to extract continuous, unidirectional work. Early industrial applications, like heavy motors and arc lamps, required a direct, continuous push. To power them, engineers had to find ways to force alternating current to act like direct current. The era's standard solution was a brute force method. Engineers injected a direct current overlay directly onto the alternating line to neutralize the reverse flow. This diagram shows a standard alternating wave overlapping with a flat direct current. The mechanical result is that the negative troughs are flattened out, leaving only the positive peaks active. You are discarding 50% of the electrical energy you just generated, making this method highly inefficient. Solving this massive energy loss required a complete reimagining of how circuits handle bidirectional flow. To harness alternating current efficiently, engineers had to stop fighting the wave's physical nature and start routing its phases. In the early 1890s, Nikola Tesla pivoted his attention away from standard generator mechanics to focus purely on circuit geometry. Surrounded by high-frequency apparatus and complex wiring, he searched for a structural solution to the alternating current problem. He outlined a specific thesis for this in Chapter 30 of his collected writings, detailing the alternate current electrostatic induction apparatus. Instead of suppressing half the wave at the source, Tesla designed a system to render the entire alternating wave available for continuous work.
He achieved this through a shift in circuit topology. Topology refers to the physical arrangement and interconnection of electrical pathways. Tesla left the generator exactly as it was and altered the physical pathways the current was allowed to take. This structural approach bypasses the need for mechanical commutators or inefficient direct current overlays entirely. Circuit geometry, rather than the manipulation of the wave at its source, provided the structural means for full wave utilization. This diagram shows a single standard alternating transmission line carrying a full bidirectional wave. Tesla's first topological intervention was simple. He divided the main circuit at a specific point into two distinct parallel paths. A raw split immediately presents a problem. The alternating current simply sloshes back and forth equally in both new branches, achieving zero directional control. To make the bifurcation useful, he needed a mechanism to dictate which direction of the wave was allowed down which branch. His solution was counter-electromotive force, or counter-EMF. Counter-EMF is an active, localized voltage inserted into a circuit to push back against a specific direction of current flow. In practice, counter-EMF acts as a one-way pressure valve for electricity. By simply splitting the path, Tesla created the physical space necessary to trap, isolate, and filter the conflicting phases of the alternating wave. Look at the split circuit diagram again. We insert a specific counter-EMF device into the top path, branch A. This first device is calibrated to actively oppose and block the negative phase of the alternating wave, allowing only the positive phase to pass. Next, we insert a second inverted counter-EMF device into the bottom path, branch B. Because this second device is configured to oppose the positive phase, only the negative impulses can travel down the bottom wire. The overall topological result is highly efficient. The single chaotic alternating line is now separated into two distinct streams of pulsing unidirectional current. Unlike the older direct current overlay method, exactly 100% of the original alternating energy is now captured and available for work. The counter-EMF gates organize the alternating current into two parallel, unidirectional streams of continuous energy. Using direct secondary generators to create the counter-EMF in each branch is mechanically cumbersome and prone to timing errors. Tesla developed an advanced variant for this system. He completely replaced the direct generators with localized fields of invisible magnetic force. This diagram shows the two branches routing directly through these dense magnetic fields. The magnetic field naturally creates a counterforce that reacts to the direction of the passing current. It acts as a passive automatic gate to block the unwanted phase. This design removes friction from the system. There are no moving parts, no commutators to spark, and no secondary generators to synchronize. The phase routing is now governed entirely by the absolute laws of electromagnetism. By utilizing magnetic fields, the circuit manages its own phases in real time, completely decoupling the alternating wave from physical mechanical limitations. To anchor this abstract theory, Tesla applied it to a specific industrial paradox, accurately measuring the energy consumption of an alternating circuit. A standard continuous current meter cannot read alternating power. The rapid reversals cause the mechanism to simply twitch, unable to register a cumulative total. Tesla solved this by routing his phases through an electrolytic cell. An electrolytic cell uses electrical energy to drive a chemical reaction, frequently used to measure or modify conductive solutions. Inside this cell, two conductors extend parallel to each other in close proximity, connected in series through a resistance. This specific physical layout maintains an equal difference of potential between the conductors throughout their entire extent. As the separated currents pass, the resulting variations in the cell's resistance serve as a direct physical measure of the total alternating energy. The final result is clear. A delicate, continuous current registering mechanism is now capable of accurately tracking the power of a chaotic alternating line. Tesla's phase routing organized the violent alternations of the wave so effectively that delicate instruments could interact with it as if it were a flat, continuous line. Zooming out from the meter, the macro-level implications of Tesla's bifurcated architecture become clear. This system's map illustrates the creation of a self-exciting alternating dynamo enabled by this topology. The raw wave is split and routed, simultaneously powering heavy industrial machinery and precise continuous current meters. It ensures the complete elimination of the 50% energy waste caused by direct current wave suppression. Tesla achieved this total efficiency without altering the fundamental physics of the alternating wave at its source. This topological framework proved that physical circuitry could sort electrical currents natively, bypassing mechanical workarounds. Tesla's architecture absorbs and directs the wave's full bidirectional power by conforming the circuit to the electrical behavior of the AC wave.
We usually picture Nikola Tesla as an unyielding purist, an engineer who designed mathematically flawless systems in the pristine isolation of his laboratory. His crowning achievement in that lab was the polyphase alternating current motor. This diagram shows resultant attraction. Firing magnetic poles in a continuous circle creates a magnetic pole that smoothly drags the inner rotor. To maintain this, the motor requires independent electrical currents, peaking at different moments to keep the push going. It operated with massive efficiency in the lab, but it had a fatal flaw. It required a sophisticated multi-current electrical grid that did not actually exist. In the 1890s, the world's electrical infrastructure was primitive. Cities were wired with a chaotic patchwork of single overhead power lines. Those single-circuit systems were built strictly to provide power to basic lighting, like street lamps. They were never intended to drive complex industrial machines. This visual comparison highlights the problem. The existing outlets only provided one pulsing back-and-forth wave of alternating current. If you feed that single wave into a multi-phase motor, the rotor doesn't spin, it just stutters and locks in place. Tesla's perfect motor was useless on the current infrastructure. To keep his alternating current systems viable, he had to figure out how to drive a machine that required multiple electrical pushes using a grid that only offered one. His first transitional fix was the Type 2 motor. This schematic shows how it worked. He took the single wire coming from the wall and physically split that single line into two distinct branches inside the motor's housing. Then he introduced a phase shift. He built one of those branches with higher electrical resistance. Because it was harder for the electricity to flow through that specific path, the current in the second wire was forced to slow down and lag behind the first. With one wave arriving slightly after the other, the motor receives a staggered 1-2 punch at the magnetic poles. This tricks the motor into spinning by simulating a rotating magnetic field. It solved the immediate problem, but it was a mechanical illusion. The motor lost efficiency by forcing the split, which drove Tesla to design a machine that didn't need to fake a second current at all. That effort resulted in the design detailed in Chapter 14 of his collected writings, the Type 3, or true single-phase motor. The engineering goal here was stringent: operate the motor on one circuit without physically dividing the wire branches inside the housing. In this cross-section of the Type 3, we see a single pulsing wave hitting the armature, the rotating center of the motor. Between each electrical pulse, power drops. Tesla weighted the physical architecture so the rotor's own physical momentum coasts through those dead spots. To maintain that delicate spin, he balanced the magnetic energies. The inner magnetic field of the armature and the outer stationary field pulse in perfect sync, maintaining a constant torque without relying on a delayed second wave. Rather than demanding cities spend millions rebuilding their grids to accommodate his ideal machine, Tesla rebuilt the physics of his motor to function within the grid's limitations. Once a factory could plug an alternating current motor directly into a standard wall outlet, commercial adoption spiked. Small businesses bypassed the need to install complex multi-wire infrastructure. They simply tapped into the existing street lighting lines to run their equipment. This localized, easy access rapidly accelerated the electrical age, allowing alternating current to light up massive public works like the 1893 World's Columbian Exposition. Because consumers at the end of the line could finally use the power easily, companies like Westinghouse could confidently build massive, centralized generators to feed the grid. The single-phase motor was the practical adapter that made the entire alternating current ecosystem commercially viable on a global scale. We often romanticize inventors as dreamers, sketching flawless concepts in a vacuum, detached from the physical limitations of the outside world. Looking at the progression from the mathematically perfect Type 1 motor to the hacked Type 2, down to the masterfully compromised Type 3, shows a very different reality. True engineering requires the flexibility to take an ideal concept, break it apart, and force it to work within a flawed, pre-existing system. That specific, grueling process of adaptation took Tesla's machines out of the laboratory and actually allowed them to power the modern era.
We usually picture Nikola Tesla as an unyielding purist, an engineer who designed mathematically flawless systems in the pristine isolation of his laboratory. His crowning achievement in that lab was the polyphase alternating current motor. This diagram shows resultant attraction. Firing magnetic poles in a continuous circle creates a magnetic pole that smoothly drags the inner rotor. To maintain this, the motor requires independent electrical currents, peaking at different moments to keep the push going. It operated with massive efficiency in the lab, but it had a fatal flaw. It required a sophisticated multi-current electrical grid that did not actually exist. In the 1890s, the world's electrical infrastructure was primitive. Cities were wired with a chaotic patchwork of single overhead power lines. Those single-circuit systems were built strictly to provide power to basic lighting, like street lamps. They were never intended to drive complex industrial machines. This visual comparison highlights the problem. The existing outlets only provided one pulsing back-and-forth wave of alternating current. If you feed that single wave into a multi-phase motor, the rotor doesn't spin, it just stutters and locks in place. Tesla's perfect motor was useless on the current infrastructure. To keep his alternating current systems viable, he had to figure out how to drive a machine that required multiple electrical pushes using a grid that only offered one. His first transitional fix was the Type 2 motor. This schematic shows how it worked. He took the single wire coming from the wall and physically split that single line into two distinct branches inside the motor's housing. Then he introduced a phase shift. He built one of those branches with higher electrical resistance. Because it was harder for the electricity to flow through that specific path, the current in the second wire was forced to slow down and lag behind the first. With one wave arriving slightly after the other, the motor receives a staggered 1-2 punch at the magnetic poles. This tricks the motor into spinning by simulating a rotating magnetic field. It solved the immediate problem, but it was a mechanical illusion. The motor lost efficiency by forcing the split, which drove Tesla to design a machine that didn't need to fake a second current at all. That effort resulted in the design detailed in Chapter 14 of his collected writings, the Type 3, or true single-phase motor. The engineering goal here was stringent. Operate the motor on one circuit without physically dividing the wire branches inside the housing. In this cross-section of the Type 3, we see a single pulsing wave hitting the armature, the rotating center of the motor. Between each electrical pulse, power drops. Tesla weighted the physical architecture so the rotor's own physical momentum coasts through those dead spots. To maintain that delicate spin, he balanced the magnetic energies. The inner magnetic field of the armature and the outer stationary field pulse in perfect sync, maintaining a constant torque without relying on a delayed second wave. Rather than demanding cities spend millions rebuilding their grids to accommodate his ideal machine, Tesla rebuilt the physics of his motor to function within the grid's limitations. Once a factory could plug an alternating current motor directly into a standard wall outlet, commercial adoption spiked. Small businesses bypassed the need to install complex multi-wire infrastructure. They simply tapped into the existing street lighting lines to run their equipment. This localized, easy access rapidly accelerated the electrical age, allowing alternating current to light up massive public works like the 1893 World's Columbian Exposition. Because consumers at the end of the line could finally use the power easily, companies like Westinghouse could confidently build massive, centralized generators to feed the grid. The single-phase motor was the practical adapter that made the entire alternating current ecosystem commercially viable on a global scale. We often romanticize inventors as dreamers, sketching flawless concepts in a vacuum, detached from the physical limitations of the outside world. Looking at the progression from the mathematically perfect Type 1 motor to the hacked Type 2, down to the masterfully compromised Type 3, shows a very different reality. True engineering requires the flexibility to take an ideal concept, break it apart, and force it to work within a flawed, pre-existing system. That specific, grueling process of adaptation took Tesla's machines out of the laboratory and actually allowed them to power the modern era.
Nikola Tesla is usually remembered for his work on the invisible, the mathematics of polyphase currents and high-frequency phenomena. But for his theoretical power networks to function, the physical motors had to survive brutal, heavy industrial conditions. The electrical revolution of the late 19th century demanded power on a massive scale, requiring machines that could run flawlessly under continuous strain. This brings us to a specific, highly practical section of his writings, Chapter 39. It contains almost no electrical theory, dealing entirely with mechanical architecture. In this text, Tesla outlines an improvement consisting of a novel frame and field magnet. He explicitly states the ultimate design goal, to render the machine more solid and compact. Why did a man obsessed with alternating currents care so deeply about the shape of a cast iron frame? And why does that iron matter exactly as much as the copper coils inside it? In electrical machine design, achieving mechanical solidity and maximizing magnetic efficiency are the exact same engineering problem. A standard dynamo from the early 1890s is a sprawling machine. It looks piecemeal, built by bolting separate magnets to a common baseplate. If we strip away the copper windings and the spinning central armature, we isolate the structural iron frame. This iron chassis has two jobs. First, it faces a mechanical requirement. It must hold the spinning armature perfectly centered. Operating at industrial speeds, the frame must withstand massive torque and rotational forces pulling at its joints. Second, it faces an electromagnetic requirement. The iron must serve as a physical conduit for the machine's magnetic field. The critical architectural flaw in early designs is that the field magnets were treated as discrete components, simply bolted onto a separate baseplate. By treating the structural frame and the magnetic circuit as two separate components, engineers built a machine at war with itself, failing mechanically and magnetically. Look at the physical dimensions of the older models. The tall field magnets stand entirely separate from one another on the baseplate. This creates a tuning fork effect. These tall, discrete iron structures become highly susceptible to oscillation. High RPM operation and magnetic drag exacerbate this vibration, putting immense stress on the bolts holding the machine together. This poses a catastrophic risk. If vibration shifts the armature off-center by just a millimeter, the rotor strikes the stator magnets, destroying the machine. Simply making the bolts larger or the base heavier is a brute force approach. It fails to solve the inherent resonance problem of connecting separate parts. A machine built of separate, bolted parts will always possess mechanical weak points when subjected to dynamic, high-speed rotational forces. While the frame shakes itself apart mechanically, an invisible failure occurs with the magnetic flux trying to travel through that same iron. This introduces the concept of magnetic reluctance. Magnetic reluctance is a metric measuring the resistance a material offers to a magnetic field, functioning similarly to electrical resistance. Iron has very low magnetic reluctance. Air, on the other hand, has a massive magnetic reluctance. Notice the physical junctions where early discrete magnets bolt to the baseplate. Between them is always a microscopic air gap. When magnetic flux lines hit this gap, they struggle to cross, scattering and losing intensity as they enter the next piece of iron. Every single bolted joint in the machine acts as a severe choke point for the magnetic field. Zooming out, the overall shape compounds the error. A sprawling, wide frame forces the magnetic field to travel a much longer total physical distance. The fundamental rule of magnetic circuits is that a longer physical path through the iron equals a higher total reluctance. Early dynamos wasted immense electrical energy simply trying to push magnetic fields through bolted air gaps and unnecessarily long, sprawling iron paths. Tesla's Chapter 39 solution completely abandons the discrete, bolted-together architecture, the physical machine transforms. The field magnets thicken, shorten, and merge seamlessly into the outer structural frame. This achieves an immediate mechanical victory. A single continuous casting eliminates bolted joints, completely neutralizing the tuning fork vibration. This unbroken, rigid casting is exactly what Tesla meant by making the machine more solid. It also achieves a magnetic victory. The unified circular shape physically shortens the magnetic circuit. The complete elimination of bolted air gaps removes the magnetic choke points. The magnetic flux lines travel in tight, highly efficient, unbroken circles. With a lower total reluctance, the machine requires significantly less copper wire and electrical energy to generate the same powerful magnetic field. This optimized, shortened iron path is exactly what Tesla meant by making the machine compact. Tesla's engineering elegance lay in realizing the physical structural enclosure and the invisible electromagnetic circuit were the exact same thing. By unifying them, he built the rugged physical foundation for the modern industrial motor.
An AC motor generates a rotating magnetic field to drag the central rotor. This requires two distinct alternating currents, phased out of sync by 90 degrees, but supply only a single-phase current and rotation stops. The field becomes a stationary wave. The rotor entirely stalls. Early electrical engineers considered building a self-starting single-phase motor mechanically impossible, unless they added clunky external capacitors or complex secondary generator circuits to fake a second phase. The greatest barrier to the widespread adoption of alternating current was not generating the electricity itself. It was figuring out how to make a single oscillating wave physically turn a mechanical shaft. Nikola Tesla took a different approach to the single-phase problem. He abandoned external circuits entirely, choosing instead to manipulate the physical geometry of the stator. In Chapter 18 of his published lectures, Tesla outlines a motor design based specifically on the difference in magnetization between the inner and outer parts of an iron core. His solution relied on isolating a microscopic time delay inherent to the physics of magnetism itself. He focused on a physical phenomenon known as magnetic diffusion. Magnetic diffusion is the process where a magnetic field takes a measurable amount of time to penetrate and fully saturate a solid conductive material like iron. Most engineers viewed this diffusion as a parasitic lag and tried to eliminate it to create a more efficient core. Tesla realized he could isolate this chronological time delay in the iron and transform it into spatial rotation for the motor. This diagram shows a solid, laminated cylindrical iron core surrounded by a standard alternating current coil. The standard textbook assumption is that when current flows through the coil, magnetic flux instantly and uniformly saturates the entire volume of the iron core. In reality, the magnetic flux originates at the outer boundary of the core. It then propagates inward toward the center over a fraction of a millisecond, acting like a wave moving through water. The mathematical consequence of this propagation is that the magnetic phase at the outer surface, point A, chronologically leads the magnetic phase at the air part of the core, point B. When we plot the magnetic intensity of these two specific regions on a graph over a single AC cycle, we see point B's wave is shifted to the right. It is lagging behind point A. The physical mass of the iron block naturally splits a single alternating current into two out-of-phase magnetic fields. Tesla now had the raw, invisible ingredients for rotation. The mechanical engineering challenge was determining how to capture these two out-of-phase fields trapped inside a solid block of iron and apply them to a spinning rotor. Tesla's geometric solution was to physically carve the iron. He structured the core so that the outer magnetic pathways routed to one set of stator teeth, and the inner pathways routed to an adjacent set of teeth. As the alternating current cycle rises, the outer poles receive the flux first. They reach their peak magnetization early. Fractions of a millisecond later, the delayed flux finally reaches the inner poles, driving them to their magnetic peak just as the outer poles begin to weaken. This alternating sequence creates a series of magnetic peaks jumping from the outer teeth to the inner teeth. It produces a sweeping directional motion across the face of the stator. By bifurcating the iron pathways, Tesla translated a microscopic chronological delay into a macroscopic rotating magnetic field, driven entirely by a single phase of current. However, this specific design had a limitation. The natural diffusion delay creates a phase shift, but that time gap is often too small to generate the heavy starting torque required for industrial machinery. To artificially widen this phase gap, Tesla wrapped thick, closed loops of copper around the delayed inner poles. This relies on Lenz's law. Lenz's law dictates that an induced electrical current will flow in a direction that opposes the change in magnetic flux that created it. As the primary magnetic wave tries to enter this inner pole, it induces a secondary electrical current in the closed copper loop. This newly induced secondary current generates its own opposing magnetic flux. It actively fights the incoming wave and severely slows its arrival into the iron tooth. This localized short circuit strategically amplifies the natural lag of the inner core. It forces a massive phase difference between the teeth, which drastically increases the motor's overall raw rotational power. Looking at the entire assembled motor, we can see the complete system operating on a single-phase AC supply. The magnetic flux spawns at the outer edge, splits, delays at the copper rings, and sweeps continuously across the bifurcated poles in a circle. The heavy, solid steel rotor is physically dragged by this engineered wave, resulting in a smooth, continuous, and powerful rotation. This continuous mechanical rotation is entirely powered by a single oscillating wave. Tesla definitively solved the single-phase starting problem without using fragile external capacitors. This specific motor design is a historical artifact, but it also represents a distinct approach to electromechanical problem solving. Traditional engineering mindsets often try to insulate against or brute force their way through parasitic losses, like magnetic lag. Tesla did the opposite. He built a passive, geometric phase shifter using nothing but the structural arrangement of raw iron and copper. True engineering elegance is not achieved merely by eliminating inefficiencies. It is architecting the system so deeply that the parasitic effect itself becomes the prime mover. Drop a solid metal rotor into a standard single-phase magnetic field, and it does not spin. It violently vibrates in place. Single-phase alternating current flows back and forth along a single axis. It produces a magnetic field that pulses on and off, but it cannot produce the rotating magnetic wave required to actually drag a rotor in a circle. In the late 19th century, the existing electrical grid was built entirely on this single-phase power. Ripping out these massive industrial dynamos and laying multi-phase power lines across cities was a financial and logistical impossibility. To achieve rotary motion without replacing the power grid, the solution had to be localized. The motor itself must manufacture a second, out-of-sync phase internally. In Chapter 15 of his collected writings, Nikola Tesla outlined a mathematical solution. He detailed how a single alternating current could be artificially divided into two parallel paths. The main power line enters the motor and branches into two internal circuits. Splitting the wire yields two identical pulses. To generate rotation, these branches must be pushed out of sync to create a measurable temporal gap. By manipulating the physical properties of the internal wires, engineers can locally sculpt the flow of time and phase without relying on the power plant. In alternating current circuits, the current naturally lags behind the voltage driving it. This phasor diagram maps that delay. The exact angle of the lag is controlled by two opposing forces. First is inductance, or L, a magnetic inertia that delays the current. Second is resistance, or R, the electrical friction. The precise phase lag is determined by the mathematical ratio of self-inductance to resistance, L over R. For the motor's first pathway, circuit A, the engineering goal is to push the current as far behind the voltage as physically possible. To maximize this delay, the math dictates strict physical requirements. Maximize the inductance, L, and minimize the resistance, R. This schematic cross-section of circuit A shows how that is built. To keep the electrical friction low, the circuit uses thick copper wire. To generate massive self-inductance, that thick wire is wrapped in many tight turns around an iron core. This heavily coiled, low-resistance architecture forces the current to drastically fall behind, firmly establishing the first delayed phase. Circuit B, the low-lag circuit, requires the exact opposite. The current must stay closely aligned with the voltage. This demands an inverted physical design. Minimize the inductance and maximize the resistance. This diagram shows the resulting construction for Circuit B. It uses very few turns to reduce magnetic inertia and employs a thinner wire to purposefully increase electrical friction. Tesla also recommended using a material with higher specific resistance, such as German silver, to choke the current without inducing any magnetic delay. By engineering these two extreme opposites, one circuit thick and highly inductive, the other thin and resistive, Tesla engineered a massive phase gap from a single power source. Altering the physical wire so radically introduces a severe mechanical risk. Designing one highly inductive circuit and one highly resistive circuit can yield one overwhelmingly strong magnetic pole and one dangerously weak one. We can see the solution in this visual equation. The true measure of magnetic strength in a pole is calculated in ampere turns, the current multiplied by the number of coil turns. Circuit A achieves its magnetic strength through its massive number of turns, which compensates for the current choked by its high inductance. Circuit B contains far fewer turns, but compensates by drawing a proportionally higher current through its lower inductance. Extreme electrical asymmetry is required to shift time, but perfect magnetic symmetry is strictly required to produce stable physical motion. These mismatched coils are then brought together into a physical artifact. Circuit A and Circuit B are wound sequentially and alternately around the circular stator, the outer stationary ring of the motor. This 3D schematic shows the moment the single-phase alternating current is fed into the combined stator. Because of the engineered L/R difference, the magnetic peaks hit pole A, and then a fraction of a second later hit pole B. The physical geometry of the stationary coils simulates a rotating polyphase power supply internally. This elegant local design bypassed the massive infrastructure requirements of building true two-phase grid generators. The rotational motion of this motor is not delivered by the power plant. It is dynamically generated by its own stationary architecture. This blueprint highlights the broader lesson. Impedance, the combination of resistance and inductance, is typically viewed as a parasitic loss to be minimized. Tesla proved impedance can be transformed into a sculpted variable. It is an engineering tool to manipulate time and control space within the confines of a single machine. Late 19th century electrical engineering faced a strict physical limit. The dominant infrastructure of the era relied on continuous current machines, dynamos that pushed electricity in a single, unyielding direction. They were heavy, inefficient over long distances, and prone to violent sparks at their contact points. Nikola Tesla proposed a different architecture, the polyphase alternating current motor. But this motor could not plug into the existing grid. It required a different electrical language, multiple out-of-phase alternating currents operating simultaneously. This created an immediate practical problem. Tesla's motor needed a complex, fluctuating wave of energy, but every power plant, factory, and grid in the world was already wired for single-output, continuous direct current. Asking the industry to replace every existing generator to accommodate one new type of motor was a financial impossibility. The infrastructure was entirely too massive to scrap. To make his polyphase motor viable, Tesla did not discard the old grid. Instead, he analyzed the standard continuous current generator as a topological problem of phase generation. The starting point was Faraday's law of induction. By definition, any electromagnetic generation achieved by rotating closed coils through a magnetic field inherently produces alternating current. The unidirectional current associated with early dynamos is the result of a specific mechanical intervention at the output stage. The machines generate alternating current internally, but that current is redirected before it leaves the housing. That intervention is a device known as the commutator. A commutator is a split copper ring attached to the rotating shaft of a generator that acts as a physical rectifier. As the internal alternating wave prepares to reverse its natural direction, the split ring mechanically flips the circuit connection. This forces the current to flow in only one direction before it reaches the external wires. A standard direct current armature, the rotating, power-producing component of the generator, is a polyphase AC source. Accessing that source simply requires modifying how the circuit taps into the rotating geometry. Let's isolate a wire loop rotating in a magnetic field. As it cuts lines of force, voltage rises, falls, and reverses, tracing a perfect AC sine wave. Now, watch as we reintroduce the split ring commutator to this loop. The split ring is timed with rotation. Exactly when voltage crosses zero to go negative, the ring mechanically flips the connection. Look at the graphical output. The negative half is inverted, creating positive-only pulsing arches, rectified continuous direct current. To extract the native alternating current and power a new class of motor, this mechanical rectifier must be bypassed entirely. Tesla's modification was reductive, discarding the commutator entirely. In its place, he introduced solid slip rings. These continuous bands maintain constant connection, never breaking the circuit. The raw electrical output flowing through them returns to its natural state, a perfect single-phase AC sine wave. This mechanical substitution changed the machine's electrical output without altering its magnetic field or its rotational speed. However, a single phase of alternating current is insufficient to drive Tesla's Tesla. The system requires a polyphase solution, multiple currents interacting in sequence. This presents a geometric problem. How do we extract a second distinct alternating wave from the exact same spinning armature? Tesla realized that the armature coil is a closed geometric loop. By connecting to this loop at specific angular intervals, different temporal faces of the wave can be isolated simultaneously. He added a second pair of slip rings, connected exactly 90 physical degrees away from the first. This chart displays the second tap's output. Because of the physical offset, its voltage peaks exactly when the first is at zero. This produces a two-phase alternating current system, derived entirely from the spatial geometry of the connections. A standard continuous current machine topology has now been retrofitted into a polyphase generator, capable of delivering the power required by Tesla's motor. The power flows from our retrofitted two-phase generator directly into a circular motor stator, the stationary outer part of the motor, which contains 4 orthogonal electromagnetic coils. Because the two currents are out of phase, their electrical peaks arrive at the orthogonal coils of the motor at different times. These staggered electrical impulses generate corresponding fluctuating magnetic fields in each set of opposing coils. Look at the compounding effect inside the stator. As the first sine wave peaks, the vertical magnetic field is at its strongest. As the second wave peaks, 90 degrees later, the horizontal field takes over. The result is a combined magnetic vector arrow that rotates smoothly around the interior space. This smoothly sweeping vector is the progressive movement of the magnetic poles that Tesla sought to achieve. The final step is introducing the rotor, the central moving part of the motor, placed directly into this rotating magnetic field. It operates on the principle of resultant attraction. The rotating magnetic field induces an electrical current within the rotor itself, creating an opposing magnetic force that grabs the cylinder and drags it along in circles. This mechanism requires no brushes, no commutators, and no direct electrical connection to the spinning rotor. It eliminates the mechanical friction and sparking that defined continuous current motors. Starting from the constraints of 19th century direct current architecture, topological geometry was manipulated to extract polyphase alternating current. This power, in turn, generated a frictionless, rotating magnetic field. The induction motor solved the friction problem, but the deeper achievement was Tesla's rigorous understanding of electromagnetic topology, realizing that phase was a function of space, not merely time. By proving the geometry of alternating current was already present inside the massive machines the world had already built, Tesla bridged the gap between the continuous current past and the polyphase future.